Okay, so welcome back to this afternoon session. This is the afternoon session of the DLT4ALL first test rollout. This is the second day. And in this section, this afternoon, we will go deeply in exploring the smart contracts, and especially with the introduction and some use cases. So this session will be in English because we will have partners from Greece, and in particular Dimitris Zvonis, that is a software engineer and student of the computer science in the Aristotle University of Thessaloniki. He is 4 times honored and awarded in smart contracts project in the past. Some names: Holt, Shanghai, Shenzhen, and Dubai. And he is also the blockchain tech expert. Let me admit one more attendant. Okay. So he is the blockchain tech expert of Gnomon Informatic, one of our partners in this project, along with also Georg Vagenas. And also he is the lead developer of Blockchain EU, that is a system for natural resource metering using smart contract integrated sensors. The second speaker, Georg Vagenas, is a marine biologist and student of aquatic engineering in the National Polytechnic of Athens. He is twice honored and awarded in smart contract projects in the past, and he is a blockchain tech expert also of Gnomon Informatics. And he was also a scientific personnel at the Hellenic Center for Marine Research and lead project architect in Blockchain EU. So before starting, probably the agenda will be slightly modified with respect to the original ones, because we will have 2 breaks. So we will have 3 sessions of 1 hour, just to try to focus your attention, to better focus your attention in the contents. So now I can leave the stage to Dimitris, I suppose. Okay.
Thank you, Claudio. Thank you very much for introducing us. I'm sorry, I apologize in advance that we are going to be presenting in English, but we don't speak Italian. I wish we did, but we don't. So this part of the lessons is going to be in English. We're going to be presenting for the next 3 hours. 2 of those hours are on me, on Dimitris, and my colleague George Vagenas will be presenting the last hour of the lessons. We are going to be running a course introducing smart contracts to you, but not just any general high-level introduction. We're going to look a little bit deeper into Ethereum smart contracts, into general smart contracts, and maybe some code. We did include some code in our presentations. And then finally talk about trust, efficiency of smart contract systems, where to use them and where to not use them. And then George has a full hour of presentations regarding smart contracts in the business landscape in Europe, in the European business landscape, and of course use cases where smart contracts are usually found to be more useful. So as Claudio said, it's going to be a little bit modified on the breaks. These 3 hours that we have, we're going to be following a more academic schedule, so 45 minutes along with 15 minutes of break, just to keep you from losing focus. And just to let you digest what we're saying, so you can ask questions and form your opinions. I'm going to begin now with the first lesson of the 3 that I am going to be presenting. This is going to last another 45 minutes. This is called C1. C1 is the first part of our lessons. Let me see if I'm still presenting here. Yeah, I am. Let me check. Yeah, the presentation is fine. So, did I break this? No. And my presenter view. Okay. So this is the first part of the lessons that we're going to be introducing, which is an introduction to smart contracts in general. So this class aims to basically provide a basic definition of what a smart contract actually is. I know for a fact that if you come into the smart contract space, you have heard a lot of definitions about what they are. And lots of those definitions are probably contradictory with one another. So it's a little bit confusing. So let's try to clear this up right away. To describe where smart contracts are actually executed, where does a smart contract, if it's a program, where does it run? What computer does it need to run? And then we will continue by providing a basic definition of what a virtual machine is. You might have heard that also in the terminology around smart contracts. To familiarize you, the students, on how to view a smart contract's internal source code, on how to actually read a smart contract written by someone else. And of course, explain common terminology used in the context of blockchain smart contracts in general, useful terms that get thrown around a lot all the time. And then, of course, showcase good practices when starting to develop smart contracts, but without getting too technical. So to begin, as I said in this intro, we need to provide a basic definition of what a smart contract actually is. I will begin by saying that Vitalik Buterin, the creator of Ethereum, and for many the creator of smart contracts, or at least the first programmer of actual smart contracts, also dislikes the term. He doesn't like it. For him, and for a lot of us also in programming, smart contracts is a bad term because it makes you think of something else. It doesn't make you think of computer programs. It makes you think of something more legal, and it kind of confuses things. So in basis, a basic definition is that a smart contract is a self-contained set of rules that lives on the blockchain and is built to control a mutual exchange of assets. You might have heard it called an autonomous daemon, or a persistent script, or an automatic enforcer, a trustless enforcer. What a smart contract is a little program, a bunch of code, of course programmed by a human, and then embedded onto the blockchain that only obeys its own internal rules, nothing external, no one else, and automatically executes the terms of a transaction, the clauses of a contract, when some predefined conditions are met, when something happens. So all that without requiring a trusted third party, without requiring no one else. I would like you to focus on the simplicity of what a smart contract actually is. It is a bunch of code deployed on the blockchain and does something when something else happens on the blockchain. And that's the most basic definition that you can get. Because this little program is embedded onto a blockchain, which a blockchain in itself is a system of transactions between users, smart contracts also are built to automate transactions between people without requiring a third party. So this is the basic definition of what you can get on smart contracts. So how do these little computer programs actually work? Well, this is a simplified view of a smart contract's creation and usage. And I would like in your head to keep an example just so it helps you work through this figure with me. So we've got, we've got a basic need. Let's say Alice and Bob Alice wants to buy an apartment from Bob. So they want to exchange an asset. Alice holds the money, and Bob has an apartment, and of course holds the digital certification of the ownership of an apartment, and wants to sell it to Alice. This can happen through a traditional legal contract, where each of the parties has another asset that the other party wants. So Alice wants to buy the apartment, Bob wants to sell the apartment for the money Alice has. So both of them, Alice and Bob, during the first stage of the smart contract cycle, during the creation of the smart contract, they sit down together and they write a smart contract according to each party's needs and conditions. The most basic of this definition is that Alice wants the digital ownership of the apartment, the title of the apartment, so she gives the money. And Bob, to sell it, he needs the money from Alice. So this is the basic conditions. Once those are filled, only then can we declare the deal to be done. On the second stage of the smart contract cycle, which is called the deployment cycle, we have written an electronic smart contract. We now deploy it, we upload it on the blockchain. it lives and becomes autonomous because we deploy it on the blockchain. It does not belong to anyone yet, but we deploy it on the network of the blockchain. Now that it is live up on the blockchain, both Alice and Bob individually and at their own time send their assets to the smart contract. So Alice will send the money, and Bob will send the digital ownership title of the apartment, of the house, of whatever you need, at their own time and individually. So every time the smart contract lives and works on the blockchain continuously, the smart contract checks its own internal code, its own conditions. When they are filled, and if they are filled correctly according to the logic of the smart contract, it performs the exchange. So the deal in this context is automatic. Once the predefined conditions of the contract on the blockchain have been met, the smart contract actually performs the deal. It sends the digital ownership title to Alice and sends the money to Bob. And this is the basis of the smart contracts creation, usage, the whole cycle. So if Alice and Bob wrote the contract, and we come to the question of who actually owns a smart contract. Well, to answer this question, we also need to answer the question of why use a smart contract on the blockchain. Well, smart contracts don't belong to anyone, not even the programmer who built them, not even Alice, not even Bob that worked together to build it. They belong to the network, to the peers of the network, the community of the blockchain. Well, the autonomy and the decentralization achieved through the lack of individual ownership of a smart contract enables them to be trustless, to be able to operate without requiring trust, not with trust, but without even requiring it, and thus requiring no trusted third parties or middlemen. Well, no trust required between Alice and Bob in the deal that we described earlier, or towards anyone else on the network for that matter. They only need themselves and the contract. It means a smart contract will deterministically execute its clauses. So, which is a kind of a big thing, especially in digital systems. What do we mean by deterministically? It is important to understand that a deterministic machine, a deterministic system, an automaton, anything, will do what it was programmed to do when its conditions are met, rain or shine, no matter what. So there's no external factors being taken into consideration as long as the blockchain lives. And therefore, the smart contract is alive on the blockchain. It's going to execute itself no matter what in the same written way every time. This determinism is stemming from the lack of trust that the system of smart contracts requires. It all stems from the lack of the need for trust. So after answering who owns it, where is a smart contract actually executed? Well, as a smart contract belongs on the blockchain, it's also executed on the blockchain in a shared and distributed way in what is called the network's virtual machine. Smart contract transactions are executed and checked on multiple nodes, which are a fancy name to call the different computers participating on a blockchain network, such as Ethereum or Bitcoin. Every computer running Bitcoin or running the Ethereum client is a node participating on the network. So every smart contract transaction, much like all other transactions on the blockchain, get executed and checked on all the multiple nodes of the network. And the results of those transactions, the outputs, as we call them in blockchain terminology, they have to match with the results of all other parts of the blockchain node system. So this is called the consensus reaching mechanism of the blockchain. So every smart contract execution, it runs multiply on all different nodes on the network, and then all those results have to be the same. And if they are the same, the transaction is considered valid. And this is part of the consensus reaching mechanism of the blockchain itself. This, of course, might seem a bit wasteful to you, running all the same transaction again and again and again and just matching. But this is what ensures safety, and this is what ensures redundancy. No single user, no single actor is ever fully responsible for the execution of a smart contract. It's all up to the network, not just one guy. Therefore, this eliminates the possibility of fraud. Well, completely Well, yes, but actually no. Smart contracts, much like any distributed system in computer science, it eliminates some problems while introducing us to whole new other problems. In our case, smart contracts can and will be executed by multiple actors on the network, as we described. So there's no possibility of a smart contract going, no, I'm not giving you your money, or no, I'm not transferring the money. It will execute itself according to how it was written. But this opens us up to a different kind of malicious approaches and security risks. We'll discuss these risks as we go, but it opens us up to a whole different set of problems. Remember, in every digital system and in everything in reality as well, every system has its pros and cons. Nothing is fully advantageous. So, before saying anything about writing the smart contract and before actually looking at code, we have a deal, we have an agreement between two people. We need to translate a contract, and we need to translate the smart contract into code that the blockchain actually understands. A smart contracts language, because it is written by a programmer or human people, is high level. The language of the smart contract is high level. In order to be human readable and of course writable, humans write in high level languages. A blockchain now is a distributed system that doesn't really care for human readability. It only cares about optimization. It needs to remain simple, fast. It needs to have specific purposes in mind. So because it runs on multiple machines, all the nodes in the network, it needs to be optimized. And as a result, only understands machine code. So not high-level languages, but machine code. If smart contracts are to remain public, transparent, readable from any point on the blockchain, which is the basis of the blockchain, as you might have heard already from the previous lessons, the smart contracts also need to avoid being obfuscated or too heterogeneous, as we say here, too different from each other. We don't want every programmer that writes code in his own different style to end up on the same blockchain and have all the smart contracts completely different from each other and have different procedures for everything. So as you understand here, a basic step in every smart contract's lifecycle is its translation from human readable code into opcodes, what we call opcodes or bytecode, machine instructions that the blockchain understands. So we translate it from human readable language to machine instructions. This ensures that every smart contract goes through a flattening step, becomes flat, a sort of filtration that eliminates the developer's own language and puts it into a specific set of blockchain executable instructions. So no matter what you write in human language, it's going to end up as a specific set of instructions. Of course, you might have heard the term opcodes and bytecode in the past, or maybe through your own research. Opcodes, bytecode, they are interchangeable terms because they are the two sides of the same code, of the same coin. They are the same thing, essentially. To offer an example on what we're talking about, the first box that you see here is a smart contract in a high-level language. It's called a pseudo language, a fake language. So this is much like what a programmer would write a smart contract to be. This is a very stupid example of a smart contract. So my colleague George calls this a dumb contract. But what it is essentially is a blockchain smart contract that when you send it an amount of money, anything, it just records it. It records who actually sent it, and then just says thank you, and just keeps it. A basic contract, but it's still under the definition of a contract. So this is the human readable part. This is how you write it. Then, during the flattening step that we described earlier, it gets translated into bytecode. You see that second box, that huge string of hexadecimal characters down there? That's the same smart contract as above, just translated into a bit of machine code. Of course, the third box down there is just the same form again. You can translate bytecode to opcode directly. All these three boxes are the same way of expressing the same smart contract. Just the first one is the human readable part, and then you actually have to translate it to put it on the actual blockchain. And to offer an example of that, it's like it's like saying the same content in human language in just different languages. If I say, hi, my name is Dimitris in English, or if I say, ciao, mi chiamo Dimitris in Italian, the content is still the same. It's just that I'm using a different language, so I am understood by different systems, by different people. So it's all the same. It's the same smart contract. Now that we have our smart contract translated and we know that it's in a machine-readable language, we know that our logic, our human logic has become machine code, we need to deploy it. Well, smart contracts operate out of an address. So we assign an address to our new contract through a process called deployment. We put the contract, the smart contract, up on the blockchain. We load up a new blockchain transactions with our smart contract code, the one we produced on the last step. This is called the deployment transaction. We put all this code in a transaction, we pay the deployment gas cost, and we send it, and off it goes. Our smart contract now lives autonomously on the blockchain, does not belong to us anymore, and is publicly available for anyone to use. Would they want to, however? This is something to discuss later on. In the case of public blockchains, most people are usually afraid of their smart contract being public after they deploy it. Well, a contract is written to help with a specific deal between specific people in mind. It's supposed to be written to be useful just to you and your users. So why would you be afraid if someone else wants to see the contract? It's useless to them. Why would they waste their time? But that's something to discuss later on. Now, to keep up with the technical terms that I want to get rid of once we actually get to the interesting parts of the presentation, but we have to refer to the virtual machine. We have to talk about the virtual machine. You have heard about the virtual machine a lot, especially if you're trying to get your first steps into Ethereum or into Neo. You have heard about what a virtual machine is. Well, simply put, the virtual machine is where a smart contract code is executed. It is embedded in part in every single node, in every single computer that participates on a blockchain network. So if we take Ethereum, for example, every computer, every node runs its own copy of the Ethereum virtual machine, the VME, as we call them, also called an EVM instance, Ethereum virtual machine instance. So it runs its own copy of the Ethereum virtual machine, completely separated, isolated, sandboxed from the rest of the computer, from the node, and smart contracts get executed on each individual instance of the EVME. And when execution results match between nodes, a smart contract's execution, as we said earlier, can be considered valid and done. So a little special place on every computer on the network, and then smart contract transactions get executed there individually, then get matched up, and that's how they get verified. The EVM is essential to the Ethereum protocol. You cannot have the Ethereum protocol without the virtual machine. That's why people keep bringing it up, even though it's a very computer science topic, a very technical topic. Well, the virtual machine allows anyone to execute code in a trustless ecosystem in which the outcome of the execution of the smart contract can be guaranteed by many, not just one system, and is also deterministic. This is what the EVM does. It allows you to run code on this shared system. The same procedures will always produce the same result, which is what we said by deterministic. Sorry for mentioning that also again, which is, again, is a big thing in computational system. Determinism is how we actually compute stuff these days. Well, when talking about smart contracts, and the virtual machines they accompany, you might have heard of the terms virtual machine stack or state or memory or storage. They get thrown around a lot. To address some of these, the virtual machine stack refers to its internal architecture on how it stores and organizes the data of the operation it needs to compute. Well, it's a stack data structure. I will spare you the details of it, but you can easily understand it. The stack just refers to how the virtual machine stores the operations. All new operations, subsequent operation sets are stored on top of each other, right? And when you actually use something, you pop it from the top. So it's a last in, first out. So the last one that went in is the first one to go out. It's just a stack data structure. And the virtual machine also needs some sort of temporary memory when executing smart contracts. which is to store local variables. Think of how a computer needs RAM to operate. It also needs quick memory to use to do its calculations for return values and all that. This memory is considered volatile. The memory of a virtual machine is considered volatile because it is wiped when it's not used. So when the smart contract execution finishes, the memory is wiped, completely forgotten, and everything is deleted inside it. Which brings us to another concept. We would want a smart contract to remember some stuff. And it would probably need to be designed to also require persistent storage in addition to temporary memory. So this is also referred to as the contract trying to store state or storing state or being stateful, having persistent storage. Of course, as I say here, you would not want the smart contract to forget that the user has previously made a payment. When the smart contract finishes execution, you don't want to wipe that information. You need to store it somewhere. So this is why the virtual machine maintains a persistent storage space for its smart contract. For every smart contract, it holds a little piece of storage just so it keeps permanent information there, the persistent information. And of course, however, the virtual machine does not allow each smart contract to look at each other's storage. Each is private to its smart contract and is only accessible and editable by the one smart contract. And this is usually referred as the virtual machine storage or the state because it stores state, its state. And individually, you can say a smart contract state or a smart contract storage refers to its own little piece of storage space in the virtual machine. So this is as the technical stuff of using a smart contract. Now, on the terminology, we will continue, and I will skip some of the next slides because this is getting too technical still, even at the start. You might have also heard the term get thrown around a lot, especially when describing smart contract systems. You might have heard of the term Turing completeness or Turing equivalence. This is a bit of a more complicated beast, as we say here. Although it stems from the very mathematics-heavy field of the theory of commutability in computer science, it is a term frequently encountered when researching smart contract development languages. This language is Turing complete, or this language isn't Turing complete. Well, without getting too technical, Turing completeness or equivalence of a smart contract language, or the VME, the virtual machine itself, that implements, of course, this language, like Solidity in Ethereum, is used to denote that it is powerful and complex enough to represent every computational problem that can be conceived in it. So it is a bit of a convoluted definition. In short, the language rules are good enough, strong enough to allow the developer to program anything and automate anything inside the language. And it is used to convey that a programmer in a Turing-complete smart contract language is granted enough creative freedom to represent a plethora of real-world scenarios in his contracts. So that doesn't say much, however, because in the last 20 years, most traditional programming languages are Turing-complete. For example, Microsoft Excel is Turing-complete in a way, and even Microsoft PowerPoint, through a trick of automation, can be considered Turing complete. So does that say anything about the smart contract language being Turing complete? Not a lot. I still say that Turing completeness in smart contract system is still a bit of a marketing trick, but anyway. So a smart contract, much like a traditional contract, before you actually use it, maybe you'd like to see the source code of it. Maybe you weren't the one that wrote it, and maybe you want access to its own internal code to see what it will do once it gets executed. This is the basis of open code. This is the basis of open code. A smart contract is publicly deployed and is fully transparent right from the start, just like anything else on the blockchain, on a public blockchain at least. Can you read it before signing it? And before transferring assets to it, can you read it? Or before executing a function of a smart contract, can you read it? Can you read it if I have nothing to do with the people that it was built for? Because if I'm completely unrelated, if I'm just curious, can I read it? Of course I can. It's just a matter of reversing the process of deployment. Instead of going from human readable to byte code to deploy it on the blockchain, we go in the opposite direction. We get the bytecode, which is always transparent, and then we translate it back, we reverse engineer it back into human readable code. This makes every smart contract easily reversible in the sense that it is always transparent. You can always read it. But is this useful? We can say no, that it is not at all useful. The flattening step that the smart contract undergoes when translated into machine code, sorry, I missed an end there, it strips it from human elements like function names or variable names, that stuff that the human programmer put in the code to help him understand what's going on as he was writing it. The flattening step, when it happens, it removes that. So when you go from the flat back to human readable, all that is eliminated, it's scrubbed. So the result of the reverse engineered code on the blockchain is very sterilized. For example, a function that is called withdraw funds is instantly recognizable by a human, but if you reverse engineer it, it becomes func, just func. Func1, func2, func3. It's useless. So what do you do if you want to read the source code of a smart contract before actually using it? Well, in practical terms, you need to get in touch with the guy that wrote it. Much like in real life, in traditional contracts, there should be no problem with finding the source code of a smart contract, because the smart contract is already intended for a public blockchain and was certainly built with the intent of being shared between parties. Indeed, you will find, even if you're taking even your first steps into smart contract space, organizations and developers utilizing smart contracts in their work usually publicize smart contract source code at the same time they deploy it on the blockchain. It's usually just publicized, GitHubs, GitLabs, anywhere. Then it's just a matter of confirming that you are reading the same contract as they deployed. I mean, you ask them for the source code of a smart contract, you find it, and then you grab the code that you found written by a human, you compile it yourself, and you produce the bytecode. If the resulting bytecode is the same as the one that you see on the live blockchain by yourself, then you can be sure that this is the exact smart contract that's going to get executed, and you're reading the same code as it's up there in the blockchain. A relation between human code and bytecode is always one-to-one and is always reversible. So, as is the case with traditional legal contracts, you should always read something before signing it, and this is the process of reading something before signing it, even in a smart contract, before using a smart contract. Is this a security risk? We ask here that storage contents of a smart contract can't be modified by anyone but the smart contract itself. We said that storage is only accessible by the smart contract. The rules of a smart contract, its code, how it regulates a procedure, however, are fully visible and fully transparent. Is this a problem? Well, I ask you in return that how would it be a problem if the smart contract is geared towards being used by public users in the first place, by public actors in the first place? It is intended for public users. So if the smart contract was developed to be useful for a specific purpose, anyone else trying to use it apart from that purpose, they would just be wasting their own time. So in open software, and smart contract and public smart contract and public blockchain, in the field of public blockchains also, transparency and publicity does not mean lack of security. This does, however, opens us up to the possibility of an attack, because our system is public and some better programmer than me might try to exploit a little problem I wrote in my logic, in my code, and try to have my smart contract do something that I did not think ahead of. But anyway, as we said, you pay something, you get something, especially with public smart contracts. And we're going to be talking about security risks in the following lessons, even today. Some useful terminology to continue with this is that, and you've probably encountered this from the previous lessons, addresses are, of course, the basic representation of a user, an actor, or an autonomous agent on the blockchain. Addresses are the basic identity on the blockchain. So this string and address might be you, might be me. It might be also a smart contract. Smart contracts are indistinguishable from user addresses on the blockchain. There is a way to know which address on a blockchain network is a user, just a simple human user, or which address is a smart contract. You just ask it if it has data. If it has data, it sends you its internal code. But this is the basic identity in a smart contract, in a blockchain world, especially as a smart contract. This might be you. This might be a smart contract. Signatures are used in the same way as you already know in blockchains. But in the context of smart contracts, I would like to mention that signed transactions and signatures are usually used for access control. Well, a specific contract, a specific function, of a smart contract may need to be executed only by a specific user, an exact signature of a user. This can be achieved by ahead of time by hard coding, which means explicitly referring to a specific address, a specific signature in the smart contract's internal code and how you write it. For example, a smart contract might only allow itself to be destroyed, to be suicided, as we say, if and only if this is asked by the original deployer, by the original creator. Only then can it be destroyed. This is an example. Another example is that a smart contract that facilitates a loan, a traditional bank loan, might require that when you run the function release collateral of the money, of the loan, this function can only be called by the banker address, which means that the banker can actually confirm that it has received the full amount of the loan, and only then can release collateral be run without it being allowed to be run by anyone. So signatures in smart contracts are usually access control. Cryptographic proof here of a smart contract transaction is the undeniable, accurate proof that a contract did something on the blockchain. This remains forever. It is used in the same way as normal cryptographic proof of transactions in between normal users, human users, on the blockchain. And smart contracts, because although they are autonomous, they act on the same data on the blockchain as regular users. So cryptographic proof of what they did is the same kind as we see in regular transactions on the blockchain without smart contracts. A smart contract transaction, as we say here, when it's confirmed on the blockchain, contains future resistant details about what it did, how it did it, how it reached that decision, and what rules it followed to reach this decision. So, and of course, what its internal state looked like at the time of execution. So every time a smart contract does something on the blockchain, it leaves proof. It never does something without logging it first and then doing it. So you can always trace it back. Well, looking up a contract transaction, a transaction hash on the chain will yield all of the above that we described here, will return all of the above, both now and forever, or as we say, computationally forever. For as long as the Ethereum blockchain or the Bitcoin blockchain exists, when you ask for the proof of a transaction, it's going to be there. So technologically forever for us. I'm going to skip this about credentials and claims. This term used to be much more frequent in the past, but right now it's not really useful. It's credentials and claims very quickly are something that you need to prove, or you need to see if it's proven on the blockchain. A positive credential is something nice. I like to think of it as something nice. Are credentials or claims that a user would prefer to reveal. For example, my degree from the Aristotle University of Thessaloniki. If it was on the blockchain, I would like that to be revealed, and I had no problem with that being public. And negative credentials that you might have seen used around in smart contract systems are claims, credentials that the agent would prefer to keep private, although it would be very useful to have for other smart contracts. For example, a bad credit score would mean that a smart contract from a bank would need to see if there's a bad or a good credit score, but maybe you don't want that to be public. It's very private information. Arbitrators are completely off the scope of this presentation, so I will be skipping that. And to finish up, to start finishing up this presentation, good practices should be considered when using smart contracts. A smart contract should not be treated like a traditional computer program. The thing is that they're not the same, even though they come from the same basis, the same root. They're not the same. So far, so much that a mental shift, we say, is required when transitioning from using classical systems or from classical systems to peer-to-peer systems, and even more so when you're using new P2P systems like blockchains. This mental shift follows the same principles of traditional distributed systems. So a classical education in computer science really helps a lot here. But on top of the mental shift required on using distributed systems, we add a few more good practices because we have to do with novel distributed systems, with new distributed systems, with advanced distributed systems that have mostly to do with security, because they're open systems. They're not just distributed closely between 5 different servers of a bank. They're completely open to the public. So we're mostly dealing with the possibility of attack and with security issues. So some of these good practices might come as a surprise. For example, in smart contract systems, you need to avoid number crunching, to avoid complex calculations, which is strange because computer systems are traditionally very good at complex calculations, and but you need to avoid them in smart contract systems. You need to avoid them like the devil. Why? Because calculation operation of on a smart contract need to be paid in advance. So the more you calculate, the more you can, the more things get expensive. So you need to think back on your design. Do you actually need to calculate stuff on the blockchain through a smart contract? Why not make a transaction and have a supporting system, a server or a traditional digital system to support your smart contract? So you pull the data from the smart contract and then you do the free calculation at home through a supporting system. So that's a bit of a mental shift that is required. Smart contract systems also need to avoid modifying contract state, to avoid modifying contract storage, at least as much as you can help it. Which is again strange because in traditional computer systems, storage is very cheap. Storage is the cheapest thing, more so than computational power. But smart contracts are the opposite of this. Editing the storage is expensive because it requires, it is one of the most complex procedures on a smart contract, because it requires changing both now, the storage both now and in the future. So proofing this is an expensive operation. So proper contract design can ensure the minimization of records modification. So you need to build ahead and avoid changing the storage of a smart contract for as long as you can help it. Only do it when required. So measure twice, cut once, which is a very general design term here. This is 2 times as important as in smart contracts, because things can get expensive fast. And of course, there's also a thing about using user claims, as we said earlier. You need to avoid storing user claims in ways that might be a hot potato, in ways that might be unsafe in the future. So always remember that whatever you do on a smart contract, whatever you store, whatever you calculate, whatever you use, will keep a permanent record, public permanent record. So what if something that you're using now might be perceived as private information in the future? Much like after GDPR, things changed a lot. So when designing, lack of forethought can come back to haunt you as a ghost. It can come back to you. And to completely finish up this part of the presentation, this is a very sobering thought about smart contracts. Are they a panacea? Are they a solution for everything? Well, as is everything in modern computer systems, every time new technology happens, there's a fetishism that comes with it. And they say that when you're holding a hammer in your hand, everything starts to look like a nail. Well, I would like to dispel any notion of that. Smart contracts are specialized tools. They are designed and they are built with a specific purpose in mind. They automate and they regulate transactions, and that's about it. To that end, of course, smart contracts have specific uses because they have specific functionality, and of course deliver the most added value under discretely specified scenarios. So good designs and discretely specified designs. Smart contracts cannot do everything, as an old Portuguese developer friend of me used to say, but what they can do, they do so fantastically well. So, as is everything, maximum added value can usually be derived through syntaxes, not just smart contracts. You need interoperability of smart contracts with other traditional computer systems supporting them. So you need interoperability to produce the maximum value. An example of that is that a library, a very usual example, a library of books stored on the blockchain is probably a very silly idea, a very bad idea. But what about a traditional digital database of the books combined with a smart contract system that handles copyrights, that handles renting, and that handles the sales of the books? So a syntaxis of these two systems produces a much better system. We heavily urge you to avoid blockchain everything mentalities because they are very poisonous. Blockchain everything mentalities, the kinds that you see in blockchain conferences, on smart contract conferences, on conferences about artificial intelligence and blockchain integration and digital future, those tend to be blockchain everything mentalities that call that everything can be done through a smart contract. No, much like anything in computer science, much like everything in computer science, much like everything in every part of science, smart contracts are a specialized tool. You use the specialized tool to do a specific job if it suits it, and you don't use it for anything else. So this was the first part of the presentation, just to give you an intro to the thing. This is our bibliography, the sources of what claims we made inside the presentation, the media attributions, and I will urge you to keep your questions until the end. Sorry for keeping this slide here. There will be a 30-minute Q&A session at the end. So I think we are done for the first part of the presentation. And I will be calling for a 10-minute break now so I can get ready the second part of the presentation. Next, we're going to be presenting an introduction to Ethereum smart contracts, just so we actually get to the meat of the meal. And thank you very much for this. I'm calling for a 10-minute break just to get my presentation ready.
Okay, see you in 10 minutes. You can also write your questions in the chat, so that at the end, I mean, you can start writing them now, and at the end, Dimitris will answer. Thank you.
Not only that, but for anyone that's still here, we will have my colleague Spiros will be sending a quiz, some self-assessment questions for the end of this presentation. And apart from the 30-minute Q&A session at the end, don't forget that you can always send the questions to Miss Elisabetta with Common Next with email if you need something to digest your question more. So it's not something that's going to be done and finished right now, but you can always keep up with the questions in the future.
Yes, thank you very much.
No problem.
And see you in 10 minutes.
Right. So if everyone is here back, I will be continuing with the second part of the presentation. And now we're actually going to be introducing Ethereum smart contracts. After talking about the boring, the technical stuff, we're going to be moving on to Ethereum smart contracts in specific. We find there's a lot of interest on the Ethereum platform just because it's one of the more popular public blockchain solutions available, especially for developing smart contracts, because not all blockchains offer blockchain development capabilities. So this is class C2, which is an introduction to Ethereum smart contracts. This is class 2 of the 9 we have prepared, not for today, do not be afraid, but in general also, including the more technically savvy presentation material. The aims of this class, briefly, is to explain the reasons behind the prevalence and the popularity of Ethereum in the smart contract market. to explain the concept of gas. We talked a bit about gas earlier, but we're going to be explaining it fully now. The concept of gas, both in the context of Ethereum and as a general principle on other blockchains, because it's not only useful for Ethereum, but it's also useful on smart contract programming on any platform. It's a very usual concept. And of course, provide you with a working example of a smart contract in Ethereum, along with a step-by-step description of what is actually going on during its execution by line. We are going to be analyzing it together, and I promise you it's not tough at all, and it will break the expectations that you might have. So let us begin by discussing the prevalence of Ethereum in smart contract development. Why is it so popular? Well, it is indeed popular. Ethereum is the most prevalent blockchain and development platform for smart contracts. Two-thirds, 66.67% of smart contracts get prototyped on Ethereum and are either designed for private or public blockchain use, either private blockchains or public blockchains, but they get prototyped on Ethereum. This is where they take place first. It is one of the most active and buzzing platforms on the space of smart contracts, and has 4 times more developers than any other protocol out there, including full-time main branch developers, which are the workhorse of developers, the main branch developers, which are working full-time on it. Why should you care for this? Why are these factors important? Well, for one, lots of core development and general protocol activity. The more people you have working on the protocol, the more updates you get, the more features get coded in, the more you have people fixing bugs and fixing the stuff that breaks, but also expanding the protocol. It's good to be part of a protocol that always expands itself and sets goals and meets these goals, not just stays stagnant. There's also a lot of communication channels for developers to ask you for help to work on their ideas, especially on Ethereum, through Discord channels, through the Stack Exchange for Ethereum, which is still active, very active. You can always ask someone when you are stumped, when you are stuck, when you have a problem. You can always find a like-minded individual of every technical background. You don't need to be a programmer to be a developer of smart contracts. And you can always set your ideas up to public view, and you can get solutions for the ideas because you have like-minded individuals to talk with. And of course, due to its prevalence and its large development margin, there's a lot of tools for development available, integrated development environments, IDEs, frameworks, toolboxes, debuggers. All those tools are offered on Ethereum's dev resources, and you actually have a lot of tools to build with. You don't actually only need your idea, and you have sophisticated, non-crude materials to work with. You have tools. And another cause of Ethereum's popularity is probably because Solidity feels familiar. Solidity is the programming language of Ethereum smart contracts. It has roots in C++ and Java, so programming in it comes intuitively, comes naturally for some programmers. It's not too far away from what you were taught in university or what you do in your work. So in the end, it becomes a sort of a self-fulfilling prophecy. When everyone is developing on Ethereum, just because Ethereum is so popular, Ethereum gets the most attention and extra growth, and the constant spotlight that Ethereum is sitting in means that everyone keeps coming back to Ethereum. So a self-fulfilling prophecy, a feedback loop where Ethereum remains the most popular platform because it is the most popular platform. There's a lot of different smart contract creation platforms. There's lots of blockchains that you can write smart contracts on, that's for sure. And development principles remain the same throughout protocols. They're not that much different from each other, at least in development principles, of course, not design. For the purposes of simplicity and for posterity, because these are lessons for the European Commission, these classes will be focusing mostly on Ethereum, and the following classes will mostly be focusing on Ethereum. Well, Another part that's very important before distinguishing between different blockchain, between the smart contract development platforms, a distinction should be made between the concepts of proof of work towards the shift towards proof of stake, and what this means for your smart contract. Well, proof of work and proof of stake refer, of course, to the usual concepts that you might have been taught so many times before. They refer to a blockchain network consensus mechanism. They refer to how network actors, users, agree all together on the validity of a blockchain transaction. Bitcoin is, of course, famously proof of work, in the sense that you need to solve a really hard puzzle to confirm transactions. And anyone faking them will not only have to fake a really hard puzzle, but will also need to keep solving puzzles faster than anyone else in the network, not being a fraud. So it's pretty fraud resistant. Proof of work is pretty fraud resistant. And Ethereum is also proof of work. Lots of networks have shifted towards a protocol called proof of stake, which is less computation heavy. And in it, multiple actors on the network, instead of calculating really hard puzzles, they vote on the validity of the new transactions coming in. And the more assets that you hold on the network, the richer you are in the network, the heavier your vote is. The thinking behind that is that you only stand to gain from the network's ongoing health and lack of fraud. And if you go against, if you are fraudulent while having a lot of assets on the network, you are actually shooting yourself in the foot because you devalue your own wallet. And what does this have to do with smart contracts? As we asked earlier, why are we presenting proof of work and proof of stake? Well, for one, proof of stake protocols tend to be faster than proof of work ones. Blocks get produced faster. What does this mean? This means that more transactions per second, because a block is just a bunch of transactions. This means that your smart contract executes its functions faster. Your smart contract is faster. Don't forget that your contract works and executes stuff and calculates stuff through receiving and sending transactions. It's all transactions. So the faster a protocol is for reaching consensus, the faster your smart contract is going to work. So proof of stake protocols usually faster. The average Bitcoin time for a new block is around 10 minutes, 9 and 20 right now. But the average Ethereum block time is 13.5 seconds. There are protocols out there beyond proof of work, beyond proof of stake, that are much faster than that too. And this makes us think, this sounds great, but why would I ever want to write smart contracts on a platform that is POW, proof of work? Well, it's a matter of asking yourself, why buy a diesel car when there's gasoline out there, gasoline cars out there? Well, it's all systems of pros and cons. Proof of work systems famously retain transparency and decentralization much better than proof of stake systems. So according to what you're trying to do, you pick the system suitable to what you're trying to do. So yeah, of course, everything is pros and cons, and no system is fully advantageous over another. Ethereum, of course, also famously plans to shift to proof of stake completely sometime in the future. It used to be January 2020. That deadline has long since passed, and they haven't transitioned to proof of stake yet. So what does this mean for your smart contract now and in the future? Because a lot of protocols undergo different, they undergo changes and shifts in their consensus reaching mechanisms. Well, for your smart contract, both now and in the future, a period where they change the consensus mechanism is probably a period of volatility, and probably a period where you would like your smart contract to maybe not work so much because it might mess itself up. But this is something just to keep in mind. Periods of volatility are usually the periods where consensus mechanisms change up. And now the meat of this presentation is the concept of Ether and the concept of gas, which is, in short, the cost of running a smart contract. When talking about transactions, either normal transactions on a blockchain or smart contract transactions on a blockchain, you're going to be hearing the term gas a lot, and you're going to hear it a lot. People usually ask, what's the gas cost for this transaction? If the gas cost for this transaction is high, what's the gas limit for calling a smart contract transaction or function? I'm sorry. People are going to be recommending that if you want to get your transaction validated faster, you just need to pay more gas, or that this blockchain is flooded with large gas costs for deploying a contract or for sending a transaction. The concept of gas is out there, and we need to understand it deeply. Gas, I want you to think of gas like gasoline in a car, and gas is Ether, or at least in Ethereum's case, it's the same as Ether. Gas is a minuscule amount of Ether, of the blockchain's main asset. It's a minuscule amount of Ethereum that is built in every transaction and is burned off in every transaction, and is considered a minimum payment, the minimum payment used to submit something to the blockchain, the minimum friction required. So it is the transaction fee. Gas is the transaction fee. Much like gas is the needed part of driving around with your car. To make a trip with your car, you need gas. To do something through a smart contract or on a blockchain, you need gas. So why? We can easily have systems without gas. Why do smart contracts need gas to run? Why is this system imposed on us? Think of gas as what you need to pay to the network so that they can calculate your stuff for you, to compute stuff for you, and of course record it forever. As we say, there's no free lunch, and you always need to pay for if someone does something for you. So think of gas as the minimum payment required. There's also another functionality of gas that you need to be aware of. It's also needed to stop people from mindlessly flooding the blockchain network with tons of just spammy, aimless transactions. If there's a minuscule gas cost in everything, that means that one transaction is going to be nothing for you. But if someone begins flooding the network, his costs are going to go up a lot. So it's an anti-spamming measure also. Gas is so important that it's an integral part of every blockchain transaction on most blockchain networks. Simple transactions, of course, cost less gas. So a simple payment between human wallets costs nothing, or might even cost completely nothing, might cost zero. Your gas cost might get refunded. And more complex transaction cost more gas. As we said earlier, it's how much you need to pay the network to compute your stuff. So simple stuff costs less, larger stuff costs more. So smart contract transactions, because they execute their internal code, they're not just simple transactions, which often requires more computational power, of course. They are usually more expensive, smart contract transactions. And of course, the more complex you make your smart contracts, the more gas they're going to need to run. So how is gas, as a concept, connected to Ether, the asset, Ethereum, the asset that costs 310 euros, and you can buy Ethereum, you can buy stuff with Ethereum. It's an asset on a blockchain. How is gas connected with Ether for smart contracts? What's the relation between the two? Well, this is coming from the Ethereum white paper. The transaction fee, the fee of a transaction, is the total is the multiplicand of gas limit times gas price. What does that mean? Well, gas limit is an amount of arbitrary units that the transaction requires to be processed. It's a sum of preset costs for any kind of operation on a blockchain, for any kind of transaction on a blockchain. For example, do not think of it too complex, too convoluted. Simple transfers have a gas limit of 21,000, and that's it. Gas limit equals 21,000. Arbitrary units, nothing, just a number. Smart contract transactions, for example, have a varying amount of operations. So the gas limit of a smart contract transaction is the sum, the addition of every little part and operation in the smart contract. So it's 21,000 plus 7,000 plus 6 plus 4 plus 4 plus 6. So it comes up to a sum of gas limit. And this is multiplied by gas price. Gas price is the maximum amount you are willing to pay per gas unit. So for your transaction, of course, to be processed to the network, you can understand this as the more you give, the more tasty your transaction becomes for the miners on the network to process it. So, and before we explain this further, when someone talks about gas on a blockchain network, they usually mean gas limit. It's usually the meaning of gas limit. So when they say gas limit is a lot, they use gas is a lot. They usually say that gas limit is a lot. So to further understand this, I want you to think of a car that's making a trip. So we said earlier, excuse me, the transaction fee equals the gas limit times the gas price. Think of it this way. Your trip cost, the cost of your car trip equals the liters of gas you're going to put on the gas tank times the price per liter of gasoline. And this is your trip cost. The gas limit of a transaction fee on the blockchain is the amount of fuel needed for your trip to reach your destination, which, as you can understand, is a constant amount. If you go from Torino to Roma, it's a set amount of kilometers you have to make, so your car will burn a specific amount of gasoline. The amount is the gas limit. It's not going to burn more, it's not going to burn less, supposedly, suppose a perfect car. And when you go from Athens to Torino, and the distance is much more, you're going to burn more gas. So gas limit is still constant, but it's higher related to how far you want to go. And of course, gas price on a blockchain is the price of liter of fuel. Now, think of it this way. Of course, you want to pay as little as you want, as you can for a liter of gasoline. But think of it this way: what if you're willing to pay more per liter of gas, and you keep raising the price you're willing to pay for a liter of gas? More and more gas stations are gonna want you to fuel your car in that gas station. More and more gas are going to think you're a more tasty customer. So gas price, I mean, the equivalence between transaction fee, think of it as the trip cost, and it is the multiplication of the gas limit, which is the liters of gas in your gas tank in your car, times the price per liter that you're willing to pay to make your transaction a little bit more tasty for miners. Gas price technically, of course, is measured in Wei. This is why you see Wei all over the place when you're researching about Ethereum, and of course not euros. You also might see kilo Wei, mega Wei, giga Wei, Gwei. Gwei is the de facto measuring spot for Ethereum. A Wei is 1 to the 10th of the 18th of an ether, so it's 0.00001 of an ether, or 1 quintillionth ether. So those, just to save those extra zeros and to make our communication more easy, we call those ways, and we call those the small denominations are intended as helpers to help us convey gas cost to one another. Other blockchains use this concept as well. You might have heard the term Satoshi in Bitcoin. A Satoshi is a Wei. A Satoshi is 1 quintillionth of a Bitcoin, as much as a Wei is 1 quintillionth of an Ether. In the previous example, in the previous slide that we have with a simple token transfer, the gas limit we set is preset as 21,000 units. And if we're willing to pay 20 Gwei, which is a rather high price right now, for every unit, we can easily calculate the transaction fee of a simple transfer to be the gas limit, which is 21,000, times 20, which is how much we're willing to pay per 1 unit of gas. And this comes up to 0.00044 Ether, which is 12 euro cents right now. So for a permanent transfer of Ethereum on a blockchain, for a transfer that will keep a permanent record on a blockchain network and will never be able to be erased and will never be able to be cancelled, and if you want that transaction to happen within the next 4 seconds, you only need to pay 12 cents of a euro. This is typical blockchain fashion, and this is the sorts of amounts that we're playing with here. And remember, this is to keep it forever there. Well, gas can also be considered as the, in a more business sense, gas can be considered the ongoing operating budget for your smart contract system. You need to calculate gas cost for smart contract deployment. This is the first time you pay gas when you deploy the smart contract. You need to keep in mind the gas cost of functions being executed on a deployed contract, because all functions executed on a live contract are also going to need gas. You're constantly going to need to feed gas to your smart contract, always sending it gas, always. And you need to know how much gas it's going to cost to store records on the Ethereum blockchain, on the smart contract storage of the Ethereum blockchain. So ahead of time, you need to take into consideration into your design how much gas that the smart contract is going to burn every day, every month, every 3 months, every quarter, and every year. So this is your ongoing operating budget for a smart contract system. And to calculate all those, there's a preset amount of gas needed for every opcode. Remember, we talked about bytecode and opcodes back then. Every specific bytecode, every specific opcode, has a specific preset gas amount. This is all comes from the Ethereum white paper, and this is set in stone. You take this as it was written. So you understand that if a smart contract is 3,000 opcodes, and another smart contract is 12,000 opcodes of varying size, of varying type, the more opcodes that you accumulate, which means the more logic your smart contract has, the more code is actually in your smart contract, and the more complex smart contract means more gas costs. It's going to cost a lot to run a bigger smart contract on the blockchain. Things aren't that bad that I'm trying to convey them right now. They're not as bleak. Remember that if you send too much gas limit on a smart contract, the unused amount is just going to get returned to you. So it's not the blockchain is not wasteful. It's not gonna waste your money. It's gonna return it back to you. And of course, large sums of gas will also be returned to you upon contract storage clearing or contract suicide. So when you kill your contract and you stop using it and you move to something else, or you deploy a new smart contract, or when you want to wipe the entire storage, this returns you the gas cost. So think of it as an investment. But as is always the case, minimalism pays off. You need to design your smart contract well, and in doing so, you keep your running costs low. Gas costs are the main cost of a smart contract company, just so you know. So to get a taste of what an Ethereum smart contract actually looks like and what we can actually build with a system such as Ethereum, we will implement, for the purposes of this example, we will implement a public voting smart contract, a democratic voting smart contract. What it will do is it will implement a public voting process where we have candidates which are collecting votes. So in the simple example, anyone on the blockchain, any address for that matter, because people on the blockchain are addresses, can vote on a candidate that is on the smart contract through a function called cast vote. So any user can cast his vote on the candidates that we have on the smart contract. And what it does is it just raises the number of the votes of that candidate by 1, just +1. Anyone on the blockchain, this is the second function, anyone on the blockchain can also inquire about the votes received on a candidate. So if you run the function total votes for, the smart contract answers you how many votes this candidate has publicly received. And of course, all blockchain users can vote freely. And the more important part is that their vote transaction is permanently and immutably, it cannot be changed, it's permanently and immutably stored on the blockchain forever as a pair of what address, what user voted for what candidate. So this will leave a permanent record, even if testing it. It will leave a permanent record on the blockchain that will never be able to be erased, and it will never be able to be abstracted or changed it will leave an immutable trace. In the end, we also make some helper functions because it is a computer program after all. We will need also a helper function to make it in the smart contract, which will just check if a candidate that the user asks for is a valid candidate, in the sense that if the smart contract has that candidate in the list of candidates inside it, it's considered a valid candidate. This is also technically part of the smart contract. So without further ado, let's see an outside design of a smart contract like this, and we will implement it. So our democratic voting smart contract. On the first step, we have the deployer of the contract, which is you. You wrote the contract, you're the deployer. And after writing it, we deploy it, we put it on the blockchain, sending alongside the deployment command, we send it a list of candidates, 3 names. We begin with 3 names. Our candidates are 3: Cand 1, Cand 2, Cand 3. Alice, Bob, and Charlie. You send this deployment command along with the names of the starting candidates, and the smart contract is actually deployed on the blockchain and grabs it has an address of its own. It lives on the blockchain, and attached to it, it also has a storage space, a small storage space only for the smart contracts, where it stores its data, which are the names of the candidates and the votes each candidate has received. So along comes voter number 1. The voter number 1 is just an address on the blockchain, a unique address on the blockchain. And voter number 1 wants to vote for candidate 1. So he finds the smart contract. Remember, he doesn't talk to you, he doesn't talk to me, he just goes to the smart contract, which is public on the blockchain. Doesn't belong to me, doesn't belong to anyone, belongs to the network. And just finds the smart contract and executes the command cast vote, while also sending the name of the guy that he wants to vote for. So he sends it Cand 1. So the contract, without saying anything else, executes the command and just goes to candidate 1, Cand 1, and just raises his votes by +1. Does a +1. So along comes voter 2. He also wants to vote for someone. He wants to vote for candidate 3. So he executes the same function. This time he sends the name Cand 3, and the smart contract itself goes to the storage and changes the amount of votes for candidate 3, Cand 3, by +1. Along comes a third voter that doesn't want to vote. He just wants to check the total votes that a candidate has received. So he just runs the function total votes for. He sends the name of a candidate, Cand 1, and our smart contract doesn't do anything. It just replies to him, the votes for candidate 1 is 128, for example. So this is the basic functionality of a smart contract like this. It just goes +1, you can vote, and you can read the results of the votes. I don't want you to be scared of this. This is the actual code of the smart contract. Of course, it's not a high-level representation anymore. It's the actual code. You can copy-paste this, and it will naturally run on the Ethereum blockchain. You can compile it yourself, no problem. I remind you that all these presentation materials will be given to you at the end, and they are copy-paste friendly, so feel free to use any part of this code. So without being too afraid of it, let's just step by step, go line by line, see what's going on here, how it gets executed, and what everything is. I want you to, first of all, ignore the first lines, just boring technical information to the compilers, just to dignify what sort of version of Ethereum we want. Ignore that. We begin by declaring the name of the smart contract that we are writing. We declare the name to be democratic voting through a command called, through the line called contract democratic voting. This is the name of the contract. On lines 3 and 4, I'm sorry, it's larger than 3 and 4, but I'm just going to call it so because I don't see the line numbering on the side. On lines 3 and 4, we actually have the two main storage spaces of the smart contract. We've got two lists, a list of candidates, and I want you to think of this, a list of pairs, which is a pair of candidates and how many votes the candidate has. So it's a list of candidates and a list of pairs of candidates and votes. These are the two storage spaces that the smart contract just needs. Then we have the constructor. The constructor is the code that we initially run once we deployed the contract, the constructor is a special type of function that only runs when you first deploy the contract. So the first time you run the contract and you put it on the blockchain, you give it a list of candidates, which is Can 1, Can 2, Can 3, and just stores that as the list of candidates it will have for as long as it remains active, which is forever. And then we just implement the two main functions. The first function is, of course, total votes for, the function that any user can use, the function that any user can use to ask for how many votes a candidate has, a guy has, which easily you just send it, you just call this function, you send it the name of the guy that you want to check. The contract itself doesn't do anything special, just checks that, hey, do I have this guy in my list? Is this a valid candidate? So it just checks the validity of the candidate if it already has it in the list. And if yes, it just returns a number, how many votes the guy has received. The second function that we implement is, of course, the voting function, which is as simple as the rest. You just call vote for candidate. This is the name of the function. You pass a name for the candidate, and the smart contract easily does sort of the same thing. It checks if the name that you told it is a valid candidate, if it already exists in the lists, and if it does, you just give it +1. So if it was 0, it goes +1. If it was 10,000, it goes 10,001. And the final function is the helper function, as much as we said earlier. It's just a function that the smart contract calls in itself. The smart contract calls itself to check if a candidate is in the list of candidates. So to check if a candidate is a valid candidate. It belongs to the smart contract also itself. I would like also, after finishing up the line by line of the code, I would also like to return to this abstracted view of the contract. I would also, I would like to tell you that, of course, there is the contract is simplistic, and there is a structural deficiency in the contract. There's a structural weakness in the contract. Because in the smart contract, we never check if a voter, if an address has voted again in the past. So that means that voter 1 or voter 2 or voter 3 can come again and again and again and go +1, +1, +1 and vote multiple times. But this is just to keep the smart contract simple enough. But I have to tell you that there is a structural weakness in the contract. It allows users to vote and vote and vote again how many times they want, which is not a very valid thing. But to begin the afterthoughts on the democratic voting smart contract, which runs intuitively, and you can just put it right now, it will run. You might have noticed that the smart contract, unlike the contracts that you are used to, did not make use of any blockchain assets. It did not make use of coins, did not send Ethereum, it did not take gas. It did not record assets, and in fact isn't even able to receive assets. It didn't create any coins, didn't transfer any coins, it didn't create any assets at all. Well, indeed, you should design a smart contract to selectively take advantage of any number of blockchain features. You don't have to take advantage of every feature the blockchain has. A blockchain is a toolbox, and inside that toolbox, there's a screwdriver, there's a pen, there's a hammer, there's a wrench. You don't need to use any of them if you want to screw a screw in or to nail a nail. You use, for your use case and your work right now, you selectively use the tools that the smart contract provides. So in this sense, in the sense of the democratic voting contract that we saw right now, our democratic voting contract did not make any use of assets, but it took full advantage of the transparency and the immutability of transactions offered by the smart contract. And of course, due to the public nature of the Ethereum blockchain, this transparency was afforded to us due to the transparency of the Ethereum blockchain, which also means it's generally accessible. So we made a democratic voting decentralized application in 45 lines of code that is owned and belongs to no single user. It belongs to the network. Is fully democratic. Is accessible by anyone. leaves permanent records and is always resistant to fraud, which I believe is a very powerful reminder of what smart contracts can actually do. Also keep in mind that functions of a smart contract are public and callable by anyone. So we either need, as we said in the example, voters can vote again and again and again. We either need to code in and design access control signatures, only allow specific stuff to be run by specific people, or we design our smart contract in a way that invoking a function is only useful, only holds value for the people you intend the contract for. For example, as we say here, why would someone want to use our voting contract if he didn't know the candidates? You can design your contract in such a way, for example, the democratic voting contract, if you want to implement it in Torino, Italy, for some local government elections. Why would I want, as Dimitris, as a Greek citizen, which I know nothing of Torino politics or local government politics, what use do I have of using your smart contract, even if it's publicly available? Why would I come to you and vote and waste a little bit of money voting for something I have no control over? So you should factor this in your design. So build around this publicity. Smart contracts are always public, but you can work around this publicity. Make them useful only for the users that you intend them to be useful for. In the end, as we say here and before we finish up this part of the presentation, I urge you to take smart contracts for what they are. They are automated, they are peer-owned scripts, they are little programs owned by the network and are made for automation. They are as complex as you want them to be and as useful as you make them to be. Use your tools well, use your toolbox well, and see if it's useful to you as you design it. Of course, this finishes up with the same kind of bibliography for all the journals or all the textbooks we used for the claims. These are the meter attributions, and I will now change up to the third part of this presentation. I'm sorry I will not have a break here. It's the final part is just another 30 minutes. I think we can power through this. Let me change up. And there will be another 30 minutes until I finish the core classes, the core lessons. So we need to stop presenting here. That was C2. We finished with C1, C2. Now we've got C3.
Can I ask a question?
Sure, but could you keep them until the end of the presentation? Thank you.
Or Dario, you can write it in the chat if you want.
Oh, that's also possible.
Wrap up the questions.
Right, I think this is it. Let me full screen it. And this should be it. George, Elizabeth, if you can see it, please tell me.
Yes, you have the main panel projected.
All right, that's it.
Yeah.
So this is the final part of the core presentation of the first introduction to smart contracts. Of course, we're going to be talking about trust. We're going to be talking about security, and we're going to be talking about efficiency of smart contract systems in the field, in reality. We're going to be talking about the concept of trust in general, but also hacks, attacks, things that can go wrong with your smart contract systems before actually considering them. This class aims to familiarize you, the students, with the concept of trust and the importance of trust and why we don't need it or we need it sometimes, to highlight the gravity of security in smart contract use and, of course, deployment, to discuss the general novelty of smart contracts in the market, what they offer, and, of course, highlight the bad stuff, highlight key hacks and security breaches in the field of smart contracts. and of course discuss the technical and market innovations of smart contracts, how useful they are and why they are useful, without of course getting too much into the territory of George and the business presentation at the end. Just more of an introductory perspective on the matter. So, to understand trust, we need to begin to understand trust. Trust, historically, has been an integral part of any contract between humans. In fact, defining subsets of trust, like in legalese, like in good faith or in bad faith, this is subsets of trust, have been part of European law for decades. So what happens when two sides of a contract have mutually exclusive gains? How can trust be enforced on a contractual deal where one party stands to gain from the destruction of another party? And more importantly, what happens when trust breaks? Smart contracts present a new way of dealing with trust. We don't need trust. The two sides can fully distrust each other for all we care. Trust isn't taken into consideration in the first place. Trust in a contract has traditionally been enforced in the form of an intermediary. So trust is enforced by an intermediary. It is provided by a trusted third party, usually in traditional contracts. So a bank, a legal firm that threatens legal action if a contract is not fulfilled, or a government with their police units or the legal units of a government, of a state, of a country. In the ongoing effort for digital optimization, as we say here, smart contracts need to remove all third parties. And we need to get as close as we can to the absolute minimum number of users required for a two-way deal. How many are those? Two, no more, no less. If we can get as close to that perfect optimization of a deal between two people only requiring two people, then we can say that we've reached the optimal point of optimization, the optimal point of performance, I'm sorry. Smart contracts take a step towards that direction. Of course, they don't reach the optimal point, but they take a step to that direction. Smart contracts are designed to trust only themselves, no one else. So no matter who built them, no matter who uses them, contracts follow only their internal code, the rule of code, their internal source code only. This is, of course, enabled by the blockchain's cryptographically secure and shared nature. A smart contract deployed on the blockchain can remain autonomous, and its law is only its own code, its own cryptographically proven code. It's the only law that the smart contract understands and follows deeply. Nothing else on the simplicity of operations. I hope it is apparent to you that a system that cannot and indeed has no reason to move astray, as we described, the smart contract has no reason and cannot move astray from its pre-designed behavior because it follows its internal code, has no need for trust providing intermediaries because it cannot go wrong in the first place. It has no need for someone to provide trust in the smart contract. This determinism in smart contract execution is one of its major value bringers. Self-enforced trust, because a smart contract only trusts itself, needs to be complemented by complete transparency. However, both actors, assuming one of them wasn't also you, the contract creator, both users of a smart contract need to be able to fully access and read the internals of a smart contract. Otherwise, it's just a black box. Prior to using it, of course, because we said we read something before signing it and we read the smart contract before using it to see what it will actually do once it's executed. And of course, the same question again is begged. Why would someone sign a contract or a smart contract for that matter if they can read? So transparency and trustlessness go hand in hand. Otherwise, it's just a black box that you can't see inside. And of course, smart contract automation and digital anarchy. Of course, we have to talk about digital anarchy. It is useful to think that smart contracts are the building blocks, the basis of a digital economy. And consider this: if they are trustless, if they are deterministic in how they execute, and if they leave behind immutable cryptographic proof about every action they take ever, we can consider a number of smart contracts, modular smart contracts, which means purpose-specific smart contracts built for something else, each built for something else. We can consider this system working together, using each other and taking input from outside users of this described network as the basis of an automated and a self-sustaining circular digital economic system. So we describe this system as above, and this the smart contracts that make up its internal design can be considered an automated, a self-sustaining, and a circular digital economic system. This concept has been described as digital anarchy, a system that needs no one else to operate and people can just freely use it. And of course has been an end game strategy for the internet since the birth of Web 1.0. We're talking about 1994 here, almost 30 years ago. This concept of digital anarchy has been described again and again and again. We just lack the technology to get there. Is complete trustlessness a pipe dream, however, as we beg the question at the end? This is also up for discussion, I think way over the limits of this conference. Maybe we'll talk about it at the end. But it's more of a question on the philosophy of smart contracts. Can a system that is used and built by unoptimized, non-deterministic humans, emotional humans, achieve true trustlessness? Or maybe a system that's used by humans will always bring forward human-related friction and human-related errors. So for us, digital anarchy might be a little bit unrealistic in the sense that even a perfect system will be used by humans, and humans are going to bring the sentimental unoptimization of what our species brings forward at the end. But this is about the philosophy of smart contracts and doesn't have to do with the technical stuff. On the matter of constructing future-resistant smart contracts, because we want our smart contract systems to not only be here right now, but to be here in the future also. Since smart contracts, as we say, are immutable, they don't change easily. And so we have some things to consider. There's no practical way of patching a smart contract after you deploy it, which is a very strange notion again in digital systems, because usually in computer systems you patch the errors after you find them out, after you deploy your system. Patches are very useful and very common. So a future-resistant smart contract, because it cannot patch itself, a proper design for a smart contract should take into consideration your needs as a business, as an individual, as a developer, both now but also tomorrow. What you will be doing, you will be needing to do tomorrow. Consider smart contract update and redeployment as an absolutely last case scenario. To destroy a contract, to update a contract, to redeploy a contract is only an absolute last case scenario. Why? Well, because you also need to repay deployment. And what happens to the old contract? The old contract, unless you actually made it so it can suicide, it keeps all the history of its transactions and might even keep a part of itself active. So you actually need to migrate all your new users to your new smart contract. All your users, old and new, to your new contract. So there's not really death for a smart contract. So updating and redeploying, last case scenario. This immutability also means that internal data, as I said earlier, I'm sorry, I was ahead of myself. Internal data is recorded forever. Even if you clear contract storage, the history of the data entering the storage is still there. So transaction history, as we say, still persists. Make sure you don't store something that you don't want to have in the future. So in your smart contract, as you're designing it, make sure you avoid storing something now that you might not want to have in the future. So avoid hot potato situation. Avoid storing something now that might be a hot potato in the future, like the information of a credit card or an identity or a digital identity. Something that a user might think that, hey, that's private in the future. Please remove it, and you cannot remove it. a future-resistant smart contract, as we say, shouldn't store something now that it wouldn't want to store in the future. And of course, it wouldn't want to handle publicly something that might be considered private in the future, or the opposite. Consider what happened after GDPR. Consider what happened after introducing the right to be forgotten. Your citizen rights of requesting that Google scrubs data from their servers. This cannot happen on the blockchain. Data remains immutable and stays stored forever. And you can't change that. So a final very important aspect in smart contract future resistance is security. What happens if your contract, handling, of course, large sums of your capital, is attacked because it's public? What if it becomes a target due to it being public, due to that same publicness? What if it becomes a target? What if it locks up due to bugs in your own code without someone else attacking it? Proper design is essential in future-proofing your smart contract against security breaches and faults. You either need to code in fail-safes, prepare for the worst by having fail-safes and have failure states that don't completely break your smart contract, or through formal verification, we're going to talk about this, of the code prior to deployment, before you actually leave it. And this way, security risks can be mitigated. There's also a point to be made about quantum readiness. Let's take it one step at a time. Formal verification is usually a marketing term. You can see firms that promise formal verification of a smart contract or promise to formally verify your smart contract for you to make it safe. You might see blockchain services running smart contracts that are advertised as formally verified. Formal verification, for the mathematically acute in the audience, you might recognize the term, is the mathematical process of analyzing an algorithm of code into distinct mathematical states and procedures, just so that you can prove mathematically if it fails or not, if it ends up in an end state or a circular state. This is a very complex mathematical process. It's mathematical proofing, and I usually see formal verification in the sense of PhD dissertations, not business applications, but some people do still believe that formal verification is a viable choice. Maybe for smaller smart contracts, but the bigger a smart contract gets, formal verifications becomes nearly not as viable. And of course, after formal verification, you're going to see a lot of people recommending, hey, are you developing your future-resistant smart contract on a quantum-ready blockchain? Should you care that much about quantum readiness? Some blockchains are advertised as quantum-ready. Maybe we'll urge viewers of this presentation to think of quantum readiness when we actually have quantum computers and not care that much about quantum readiness right now, and just having a smart contract that actually works and is well designed, and not care about quantum readiness that much. We're still decades away from usable quantum computers. But generally, smart contract security is a gigantic topic, and we're going to be talking about this later, and of course, during the Q&A session, I'm sure some of you will have security-related questions. All in all, very quickly, constructing a future-resistant smart contract is usually a game of balance between risk, between opportunities, and between security. So, if you want a smart contract that's very exploratory of new opportunities, of a smart contract that's breaking new ground, very innovative, you're straying away from security and you're taking bigger risk. So, if you want maybe your smart contract to be more volatile or to be more risky in how it handles assets, that strays away from opportunities and security. But if you want a secure smart contract that's not going to break, it's not going to be very useful, to be honest. So it's all a game of striking a balance between these three factors. And now on the importance of security in smart contract systems. Well, security considerations in smart contracts are what we say doubly as important as they are in traditional computer systems. Why? Well, smart contracts are autonomous and they directly play with assets. They directly play with important assets. They play with money. They play with company assets, with personal assets. Bad design choices, lack of forethought, not building a smart contract to be resistant to certain attacks can and will deterministically come back to haunt you. Failing to write a good design, failing to think ahead, failing to build around known smart contract attacks, failing to consider attacks can and will lead to things breaking. And when things break, they will usually break catastrophically. This is something to consider. And keep in your mind always, good design is doubly as important in smart contracts as it is in traditional computer systems. Of course, smart contract autonomy, as we said, means that the smart contract does not belong to anyone, not even its creator. After you deploy, it's on its own. In the case of asset loss, due to attacks, due to hacks, due to logical errors in your own code, due to your own mistakes, there's no third party to save you. There's no bank to save you. There's no reversal of transactions. Everything is final. And there is no opening the hood of the deployed smart contract to fix what went wrong. There's no patching. So mistakes in smart contracts should always be considered final. And they will also be recorded forever in the blockchain just to taunt you, to make fun of you. They will be recorded forever and are final. A developer's onus, a developer's responsibility, the onus, is therefore perceived to be double in smart contract. To build a smart contract that performs a function, a need correctly, but to also proof it, to make it airtight from all possible fault scenarios, not only now, but in the future as well. And I'm sure you can understand the importance of the double importance of security, of secure design in smart contracts. And to illustrate that, we're gonna be borrowing a concept from the U.S. Army manual for infantrymen. So, famously, the old U.S. Army manual for infantrymen, when training infantrymen, it used to say that when the pin is pulled, Mr. Grenade is no longer our friend. This is exactly the same case in smart contracts. You're gonna find this principle. It's called the grenade principle. It's very usual in smart contracts. When the pin is pulled and when the smart contract is deployed, Mr. Smart Contract is no longer our friend. And this is as simple as that. When you deploy a smart contract, when you throw the grenade, power flattening occurs. When the contract is deployed, the creator is reduced to the same power as any other user. So if you make it into your design to be able to control your smart contract can and will fail on you and work against you. So not your friend anymore. Now that we've talked about the concerns and the bad stuff and the security of the smart contracts, let's talk about the advantages they actually bring to the table. Well, scientifically, most boringly, smart contracts and the blockchains themselves, they are a continuation of the ongoing advancement towards optimization in computer science. Generally, blockchains weren't born out of nowhere. They are a continuation of other concepts in computer science. Just the tip of the spear. Electronic distributed systems and ledgers, DLTs, much like we're doing right now, have been defined and have existed in more local scales in computer science for decades now. Visions, of course, of a planet-wide unified computational system to connect all the world's dealings have also been part of the field for some time now. It's been a pipe dream for programmers, for cyberpunks, for cypherpunks also for some time now, of this pan-planetary Earth computational system for all the world's transactions. This is what a blockchain is trying to achieve through smart contracts. And smart contracts acting on blockchains are the first large-scale implementation of a generalized electronic transaction peer-to-peer system. So the combination of smart contracts and blockchains, they form an accidental megastructure, as has been described in formal literature. Accidental megastructure in the sense of a network so useful that everybody wants to use it and expand on it. So accidentally, we formed a megastructure. So this is the scientific importance of the thing. Regarding market significance, though, smart contracts primarily, first of all, are cheap to run. You only pay one-time deployment cost and then the gas cost of constantly running some functions as much as your design says. That can also be passed to the users. Don't forget that you running a smart contract transaction, you running a function on a smart contract is exactly the same as any other user running a useful function on your smart contract, on the smart contract that you deployed. If they want to do something, they probably have to cover the gas cost themselves too. So sometimes gas costs can easily be passed down to the customer. And of course, you have no running cost to host the system up, to keep it digital, to keep it up, or you have no added cost of keeping permanent records. The system naturally keeps permanent records, and you also don't have the responsibility for that. It happens automatically for the future too. These systems are generally fast. We've got second or minute scale confirmation of contract transactions, and of course, these transactions are kept forever. I know some of you are familiar with digital systems that act on the order of milliseconds, but consider that in a few seconds or in a few minutes, a smart contract not only performs a function of a transaction, but also can be considered completely final and keeps a permanent record on the blockchain. So you pay a bit more time, but you also gain a lot more. And of course, smart contracts on the third part are modular. Smart contract development languages are powerful. You have the ability to represent a myriad different use cases through them. It's up to the imagination of the programmer to build whatever he wants on them, as long as it's good. And some of the less market viable traits that you're going to be seeing around are, of course, the complete transparency of operations. Useful for some, not very useful in business usually. You don't want everyone to be able to see your order book. And of course, the resistance to attacks, if designed well. Resistance to attacks is not usually a very marketable trait in the sense that a business wouldn't want the system to be public anyway. So if you end up using a public system, if you end up making a system that is publicly available, a smart contract system is very resistant to attacks if designed well, because it borrows strength from the community. When someone in the community of a blockchain, in Ethereum, when he messes up, he teaches us valuable lessons and teaches valuable lessons to the rest. And the network as a whole fortifies itself in the future and becomes stronger. We said it earlier, this is called an anti-fragile system. The more you hit it, the stronger it becomes instead of breaking. Because the community learns and the community patches and the community protects itself in the future. So the more it breaks, the stronger it becomes. And now, market-wise, smart contracts have a tendency, of course, to disrupt and to unlock value by making intermediaries obsolete. You cut down intermediaries. The value locked by intermediaries is now unlocked. So new value streams are unlocked. The self-sovereignty of code, automation capability, and their trustless nature, as we say, free up the locked capital, the needed capital of intermediaries, and allow for development cost effectiveness in development by cutting down the necessary costs. Of course, IBM and the World Trade Organization have pinpointed the major advantages of using automated smart contracts as speed of transaction confirmation goes down from days to seconds. We have increased trust between suppliers, partners, consumers, all parts of the ecosystem. IBM also notes the reduced enterprise risk through traceability, through being always able to trace what went wrong and what transaction went in and out. And of course, the capability for massive collaboration due to modularity of smart contracts. You can have specialized smart contracts working each other and forming as big systems as you would like. This is how let's talk about how the landscape of smart contracts looks right now, because it's not all happiness and rainbows. Blockchains are actively being implemented in the most relevant markets that you see here. Personally, I'm more well-versed in the fields of energy and public services, but healthcare, financial services, logistics, supply chain management, rentals, and insurance are all big markets for smart contracts. Total capitalization of these impacted markets of course, is very general and inflated. It's in the order of trillions of USD. But Ethereum, let's talk about Ethereum smart contracts alone, are expected to reach a market value of 300 million. Not a lot, but just for Ethereum smart contracts, not the structures behind them, that's a big amount, just for the Ethereum smart contracts alone. Of course, like the development of the internet before blockchains, blockchains and smart contracts are in many ways still looking for solid footing outside of early adopters. And this is true. When was the last time you saw a large-scale smart contract system being used out in the wild? Apart from the objective technical advantages of smart contract systems, they require a complete change of traditional business models. They require you to trust peers, to trust code, and to trust the network more than you trust monolithic entities, more than you trust banks, or more than you trust governments. They require a complete change of traditional business models. That's why more startups are doing it instead of classical enterprises. Apart from the technology level solutions that exist right now for smart contract development, there's also platforms for enterprise-oriented solutions being developed by, of course, the Hyperledger project, with products such as the Hyperledger Sawtooth, Hyperledger Fabric, all built by the Linux Foundation. We've got the Ethereum Enterprise Alliance, which makes a clone of Ethereum directed towards enterprises, which means maybe it's not that public. Maybe you don't want it to be public. Maybe you don't want consensus to be as slow. Maybe you want something faster. So it's like bespoke and personalized solutions for each enterprise. We've got, of course, the Corda, which is a product by R3 Corda, also an enterprise-oriented solution. And we even have cloud computing providers that offer blockchain solutions with smart contracts, such as Amazon Web Services. So the difference in enterprise solutions, I was ahead of myself there, is this, that public blockchains usually offer transparency, publicity, and somewhat slow consensus. Maybe you remove some of that and you build internal blockchains, not as democratic blockchains, that solve a specific solution inside the business. So enterprise-grade solutions, not public. And how the landscape, of course, for smart contract is looking right now. There are scarce and far between examples of corporations using smart contracts on a large scale. And this is unfortunately true. The industry is still taking baby steps. 6 years after smart contracts have been initially introduced, we're still taking the first baby steps. Although 53% of German and UK corporations, and I do not know about Greek or Italian companies, I didn't have data for that, but from my personal experience, the same situation is also reflected here. All these 53% of German and UK corporations have raised blockchain adoption in their top 5 strategic goals in the next 24 months. So the landscape is still populated by smaller scale businesses, however, mostly startups or subsidiary companies of bigger incubators and consortia. Moreover, most of these companies are offering blockchain as a service solutions for other businesses. So adoption data, I think, is a bit muddy, a bit inflated, not real. To further convey that on a more technical level, of course, you know about Stack Overflow. The developers, of course, see Stack Overflow as the second coming of Christ, but generally you are aware of Stack Overflow. It is a place for developers to talk with each other. Apart from technical stuff, they also discuss statistics of the business. So on the more technical side, on Stack Overflow, from developers by developers, its users, which are primarily software professionals, showed that 80% of the organizations that they worked in do not use blockchains or smart contracts at all. They don't use them at all, with only 12.7% of them using them for non-financial solutions. So there's another 4% using them for financial solutions and some spares. So the field is still unripe, still hasn't advanced as much as we were expecting it to rise, still taking baby steps. Well, maybe there's a reason for the industry's side steps, and this is what we're going to be presenting for the end of this presentation. We're finishing up here. Not every road is paved with roses, I would say, and there's a lot of cautionary tales in the space of smart contracts. major hacks and attacks in smart contract systems that we're going to be discussing, and we're going to be finishing up in a few minutes. Do not worry about that. Should act, our presentation here, should act as a practical lesson to further convey the importance of proper design and security testing of a project smart contracts, in your project. We don't want to scare you off using smart contracts, but I would like to illustrate the dangers of using smart contracts so that you build better designs. So we're going to begin by a starting example, a very easy example, the starting example of a system going oops and losing money. This was the example of a community casino on Ethereum where the users could guess dice rolls ahead of time. We're going to move on to the parity multi-signature wallet hack, which was a bit of a high-profile hack, a breakage, an attack, you could say, that caused 89 million euros at today's value, 500,000 Ethereum. It caused them to lock up completely and be lost forever. And of course, it couldn't be a smart contract security presentation without, of course, discussing the mother of all smart contract hacks, the DAO hack, of course. It was the largest hack in the history of smart contract in digital systems as well. The total cost of the attack was more than 500 million euros, 613 and 2,100 million at today's value, 600 million, I'm sorry. So to easily begin with a small example of how things can break in your smart contract system, this case of the transparent casino, they call it the transparent casino. It was a smart contract, quite old, 2016, and the creator has tried to erase all his traces, probably because he's ashamed, but archives of the attack still remain. It's difficult to find, but we did find a lot. The premise of the smart contract was simple. A developer created a smart contract which implemented a casino. It only had a simple game of roulette, a smart contract that implemented a game of roulette on the blockchain, on the Ethereum blockchain. The premise was good. The dice rolling process was transparent. It was fair. So you build trust with players because you were absolutely sure that the smart contract casino could not cheat, could never cheat, in fact, because it was transparent in how it produced the dice rolls or the roulette rolls. I'm sorry, I'm not so familiar with casino systems. The creator fee was just was a stable and fixed 1.5%, which means the house kept 1.5%, and this was cryptographically proven, meaning that the casino could never hold more than 1.5% of the money. That's the commission, and that was transparent from the start. Apart from the above, the creator had no other influence on his contract because remember, he deployed it, he made it, but it no longer belonged to him, and just the smart contract just worked the way he coded it, the way he designed it, and he had no other influence over the contract, just 1.5% of all the takings. And the roulette game was fully automated. So after he built the smart contract, the creator, I think a young Korean guy, I don't remember his name, I'm sorry, the creator loaded up the smart contract with 150 Ethereum, which is right now a bit more than that, let's say 25,000 euros. It's around 30,000 euros now because the price of Ethereum has been raising. So he loaded up the smart contract after deploying it with 25,000 euros because you needed a starting pool for the bets, and he deployed it. Within 2 months, it was drained clean, completely clean. The RNG seed, which is how computers produce random numbers. There's no random numbers in computers. You use a technique called RNG seeding. Because of the transparency of the smart contract, this process of producing random numbers was also transparent because the entire process was transparent. So the attacker used this kind of non-obvious vulnerability to calculate winning dice rolls ahead of time and then bet on the winning dice rolls. So he drained all of the casino clean because he was betting on the surefire wins, the dice rolls that were expected to drop in the future. He got it right 100% of the time. This, of course, fortified the community even more because after this hack, there were techniques to mitigate that sort of thing. So again, anti-fragile system. Moving on to the hack of parity. Parity is a wallet service, still exists today. They didn't go in, they didn't close up after the hack. It's an online wallet service, and it was there since Ethereum started. It's very old also. It is quite popular. I think it's the second more popular wallet for Ethereum. And one of the types of wallets it offered was a multi-signature wallet. Think of a wallet that you have with your wife or your husband that you love very much. Instead of having an account with money that any of you can use anytime, it's a wallet that requires the signature of both of you to do something. So if you want to buy something, you need the signature of both you and your wife or your husband to do something. That is the basic premise of a multi-signature wallet, so you can't control it. Think nuclear keys on nuclear submarines, or the account between husband and wife. The smart contract that handled Parity's multi-sig wallets, multi-signature wallets, promised, of course, transparency of operations, autonomy, because Parity had no control over user funds. This was all done through a smart contract, just coded by Parity. And of course, speed, because it was all done on the blockchain. As part of the lengthy design process of the smart contract, the smart contract they did was written to rely on some external code pieces they called libraries. Programmers among you in the audience already know what a library is, very usual, which are a great programming concept. Instead of reusing code, you just write one library and just reuse that single library. So it improves readability of code, it improves performance. It's a good thing to have. It's a good programming concept. Libraries, though, nobody thought of that. Because of specific blockchain particularities on the blockchain, libraries are also smart contracts, which mean they have an owner. One of the libraries of the 20 different libraries that the Parity smart contract relied on was, by mistake, left ownerless. When they deployed it, they didn't set an owner. So a user, and after finding his results, he was a newbie. He wasn't someone who knew what he was doing. He was just messing around. He was able to hijack it. He went in the smart contract, in the library smart contract, and he just made himself the owner of the smart contract. And after that, he didn't gain any money out of doing it. He just pressed the button and just made himself the owner of a useful technical library that another smart contract was using. He didn't gain any money because, as you remember from the previous presentation, storage spaces and money are smart contract specific. So the library, although it was used by the multi-signature wallet, did not have money, did not have access to the other storage, to the money of the other smart contract. So he made himself the owner of that for no reason and for no gain. And he then began pressing buttons, as young programmers usually do when they're excited that they did something that they shouldn't have. He began pressing buttons, and one of those buttons was the self-destruct button. He told the library to commit suicide. And the library, of course, followed the instruction of the owner and committed suicide. And of course, because the Parity multi-signature contract relied on that library to be alive, and every time the Parity multi-signature wallet now called the library for help, to help it with the code, and it was dead, meaning it would return false, it was failing. Every piece of Ethereum, every piece of money handled by the multi-signature smart contract was locked up forever. Up until today, there's 89 million euros completely locked up, 513,743 Ethereum completely locked up, user funds, all of them, and nothing can be done until the end of time. Frozen until today, and will remain frozen until the end of time, or until the end of Ethereum. So that's a pretty big oops on the part of Parity's developers. And finally, we come up to the biggest cautionary tale of smart contract related hacks and attacks. We come to the mother of all hacks that took place on smart contract systems, and the attack that has the most to teach us about our own smart contract systems. Things to be afraid of, or not afraid of, to be cautious of. Well, the DAO 2016 was a venture capital company designed to operate as a DAO. There's a bit of confusion with the name and the terminology. I do think it's a very unusual name, but work with me here. It was designed to operate as a DAO, a decentralized autonomous organization. So it was a decentralized autonomous organization that was named the DAO. Anyway, the definition of a DAO, of a decentralized autonomous organization, is that it is fully governed by its investors through smart contracts, is completely automated in its processes, and doesn't need a physical location or a base. It's an organization, a company that operates fully on the blockchain. It doesn't need to follow the legislation of any one country. So it's completely free on the blockchain to do anything. So the business model was so innovative that the crowdfunding stage of this company, made through an ICO, it managed to gather over $150 million. This is the largest crowdfunding round in history. It gathered, I think it gathered $165 million, something like that. It was the biggest crowdfunding campaign in history. So innovative was the business model. The crowdfunding itself was performed through a smart contract. So they set up a smart contract to gather all the funds and to later unlock those funds towards the company after the crowdfunding, the seeding round. Inside the smart contract for the crowdfund, a minor design error, just a switch around in some lines, in a code structure, left a small opening for an attack that was later called re-entrancy. It was a simple, confusing, and very niche way to execute a smart contract function more times than was expected by the original developer. There was also a second bug, but I would not like to get too technical here. But these two bugs exploited together in a very smart way. We believe the attacker of that was a mastermind of that. The attacker exploited the two bugs together to make the smart contract run itself and call itself multiple times, and the resulting combined attack allowed the hacker to drain it completely. So the attacker, after the crowdfunding, managed to drain 3,641,000 Ethereum, today's value of over $1 billion, €1 billion, 626 million euros for himself, fully drained it. The hack was so extreme that Ethereum developers even stepped in. They couldn't let it go because it was devaluating the network of Ethereum. It was devaluating it, and the Ethereum developers stepped in with a hard fork to return the stolen funds. They couldn't do anything else. The decision for a hard fork to reverse the blockchain is still causing turmoil and dividing the community even today. It was a very hard decision to work the blockchain in reverse, which made us think that maybe it's not as decentralized as they want them to say Ethereum is, but it was for them a necessary choice back then. It was a very large-scale attack. The 626 million euros was more than 60% of the total market cap of Ethereum, so a very big, large-scale attack. And of course, the hard fork is still dividing the community up until now. This is the biggest attack that has ever taken place on Ethereum and in any blockchain system in general. Of course, the bibliography of all the security issues, the attacks, is all here, all freely available. We only used open source material and open data, and media attributions, like so. And this is the end of the third core presentation. We'll stop presenting this one now. This was the end of the core material. I will now leave the space for George Vagenas, my colleague, to present business cases on the matter.
So, greetings to everyone. My name is George Vagenas. I'm a part of the Gnomon team in the DLT4ALL project, and I'm working as a blockchain designer and project manager in the blockchain smart contract blockchain system. And my field of expertise is environmental biology and data flow and analytics. Today, we're going to have an overall discussion about smart contracts in business from a market standpoint. I'll try not to monopolize the topic, so I will strive to share with you all the main highlights regarding the utilization and the usefulness of blockchain smart contracts. In the previous lectures, and I'm referring to the core lessons C1 to 3 that my colleague Dimitris just presented, he made an approach in the smart contracts in general by focusing on the major disciplines. Now, we're going to have a realistic approach in the today's utilization in business arena. The lecture is estimated to last around 45 to 50 minutes, and you have the ability to ask online questions, but it would be really great if you manage to keep your questions for the end of the presentation, so you can all the time update your queries. There will be plenty of time so we can proceed in a productive interaction. Now, I'm going to briefly explain the main objectives and the goals of this presentation. We're going to, as I said, around 60 minutes is the lecture, and I think it's worth it. And this class aims to discuss, firstly, the relational utility and the major use cases of smart contracts in the business arena decade. The most important thing that I want to say here is that smart contracts may exist as a theoretical concept since 1994 from Nick Szabo, but turned to a real-life tool since Ethereum was created, and was created by its creator, Buterin Vitalik, which he started to utilize them. Then we're going to present the workflow of an enterprise smart contract application, or DApp, in detail, which I think is the most important asset of this presentation, because will give us the ability to realize the approach that should take place when we want to work or handle smart contract operations and ideas. Then I will present quite briefly the current legal framework around the implementation of smart contracts. It's still an immature field, and it's very important because legal framework around this novel technology will define the future of this market. So it's actually crucial to discuss about some current theoretical themes and some EU legal concerns and potential future steps. Finally, I will present the main challenges that an investor should be aware of during the design of a smart contract project. Challenges and traps that should be mentioned to give you an idea about the dangers that exist. So we start. How smart contracts elevate the international business landscape? Since the mid-50s, an exponential development of information technologies and its industry took place at a global gradual scale. The creation and the utilization of the internet as we know it nowadays was the main determinant which expanded this already successful tool of modern humanity. In numbers, a report of the International Data Corporation showed that global IT industry is expected to have $5.2 trillion US net worth during 2020. Of course, these estimations were prior to the Corona period. In a regional level, Mediterranean countries act as a key player in this market by gathering almost a quarter out of this huge amount. The real value obtained through the IT industry is even bigger if we consider the academic and research impact that EU countries have on the global development process. A new tool that has been given the last decade is blockchain technology, and its most famous asset, smart contracts, came to reshape conventional industry and business operation as we knew them. So the question remains, how smart contracts will elevate the business landscape? As Dimitris said, and as it is in real, smart contracts are a bunch of code lines emptied onto the blockchain and enable agreement via contractual terms to be executed automatically without the intervention of a third party, broker or banker. Afterwards, every transaction is permanently stored onto the blockchain, which leads to where? Actually, it leads to a peer-to-peer globalized market. Individuals in a network where they can create dynamic and secured transactions in our case, in order to optimize the current status of business. How this can happen? Two notable review works took place from Wang and others at 2018 and Zeng and others at 2020. You can see the references at the end, the references sector. They revealed all the additional benefits of smart contracts in an operational manner. Finally, Three are the main axes that support the structure of smart contract technology with its benefits. Reduction of risk. As Dimitris said, there is permanent storage. This means that sensitive data are immutable and then thus are secured. We have transparency and accessibility of the data. Anyone with the right information, with the right hash or address, can access and get a transaction list under the frame of anonymously transactions, which we can approach them as pseudo-anonymous transactions under specific steps of coding, and thus can support data protection, while at the same time information belongs to a centralized network and not in someone's server or a company server. Traceability of transactions and thus traceability of each expressed product can happen through this permanent record of transactions. Then auditability, which is the ability of an account's inspection inside a business or a governmental state, or even in between them. And thus, no need for trust can be achieved. Except the reduction of risks, we have a cutting down of costs. As Dimitris said, and this is mentioned in the two papers that I've said before, we have reduced transaction costs. We have the ability through smart contracts to have rapid enforcement of costs, of penalties. And at the same time, administration fees are reduced. Everything is fully automated and decentralized. At the end, we have additional efficiency. We have a reduction in time delay. We have increased operational flow, and we have the ability to proceed in an advanced microdata analysis. And eventually, we can succeed in the integration inside a wide network of collaborators and partners with a variety of cross-functional utilities. Now, in order to be specific, we have to identify the main major smart contract use cases in applied operations. This job has already been done by Salmero Manzano and Manzano Agugliaro 2019, where they ran specific analysis in the large database of Scopus. As we see in the figure below, they found that computer science, engineering, and mathematics had the majority of the use cases, something which can be easily described as obvious. By being a bunch of scripts, as we've said before, the first and the most related sector will be computing, engineering, and mathematics. The next applied sector is energy, which is the fourth in the figure, and the fifth is business management and accounting, or supply chain management, as we will see in the next slides. Then natural sciences follow up, with medicine being the 10th most well-known application use. And then economics and finance represent the second smart contract major use case in the research field. It's important that it's in the research field. It is interesting that finance, cryptocurrency market, let's say, is indeed the biggest market around blockchains. But the applications on finance and economics are actually behind the computation arena. This shows that we're still passing through the theoretical era, and we're heading towards the applied and operational age of blockchains. Last but not least, environmental, agricultural, and biological sciences, which are connected with primary production, are an immature field for developers. And we believe as a team that there's a key there for sustainable production and integration of smart contracts in real-life solutions, in real-life problems. Let's start with the energy and smart contract metering. As Bernard Mart stated in his book, blockchain, as Internet of Value, was created itself to transfer value, any kind of it, anywhere in the world. This is probably the most important thing I want you to remember from this lecture, and start thinking about blockchain more as an interconnected layer of value instead of just a platform of transactions and for transactions. How we're going to transform, though, values of products into assets in order to find the in-between space of innovation. Last year, Matthias Lang published a significant work about the connection of smart contracts with the energy sector. In conjunction with his findings and current knowledge, energy as a physical asset can be expressed as a digital asset, and then stored, transferred, recirculated according to its design. Furthermore, through a market standpoint, small-scale producers, for example, non-renewable energy in non-renewable energy production, or even more someone that stores energy, can utilize smart contracts, and it happens as a distributional network, replacing that way the need for energy suppliers, as we said before, the third-party intermediaries. An important use case was the Brooklyn microgrid project in the US, where with the use of smart meters into the electric grid and with the simple but efficient use of Ethereum smart contracts, they succeeded to create a peer-to-peer market of energy faster, cheaper, transparent, and secured. In simple words, if Alice has some spare batteries, as an individual peer player, she can ask for Bob if he needs some energy, and through this distributional network, she can transfer this specific amount. Now, energy and smart contract metering once more, but with natural resources, which are an expression of energy, just like water itself. Very briefly, less than 2 years ago, our team started to develop a smart contract platform aimed for the water management in China, in the Yangtze region, one of the most productive regions in the world, and is, let's say, estimated to have an annual revenue around $4 trillion US. We approached the design through an interdisciplinary manner where blockchain and aquatic sciences were combined. We had some milestones. It's not that important now, but the important thing is that energy and natural resources selection was an important determinant that gave us a competitive advantage in contrast with similar projects that had other use cases. Here you can see our design in general and in a through a simple abstract. We've created an interconnection smart contract layer that connects government, which represent the wallet, which issue assets in a circular flow inside the system. We have the industries, which are the users of the system, which utilize the assets that have been given by the government. We have the wallet of research, where they keep the data and they operate as a security filter and they gather sensitive data. And of course, environmental zones, which are the production sector, which hold the overall capacity of assets. And we approach it as our nexus, our resources nexus. We started working 2 years ago with waste token, with water token, that were the first assets that we worked with in order to highlight water and pollution management. Further information can be found on our webpage. Now, let's pass to an original business-oriented sector, the field of supply chain management. Supply chain management can be defined as the exploration of different utilities that can and will optimize cross-company business processes and are characterized by 2 axes. First, downstream flows of goods and services. For example, the delivery of a smartphone from the manufacturer factory to the supplier, and then to a potential client. And upstream flows of information and finance. For example, the cost of the whole operation in a form of a ledger. We realize that supply chain hides the world chain, and we do have similar form in the structure of blockchains. The connection is apparent, but why smart contracts can be useful in this field? Actually, blockchain is a distributed database, can be approached as one, and is compromised by a list of cryptographically connected transaction blocks. Smart contracts, a tool in blockchain, are encoded contractual agreements which are activated when a type of transaction occurs. The connection between them into supply chain management. Smart contracts are simple scripts that allow mutual parties to do business in a deterministic way. Whenever a specific transaction takes place, another transaction will also happen. In other words, a chain reaction of useful data through these smart algorithmic account holders. Thus, we can achieve automated, secured, fast, inexpensive mutual agreements by removing the human error bias. But let's talk with numbers. Walmart, we all know this huge company, ran a pilot implementation project and stated that blockchain applications help the company to reduce the time needed to track, you remember, traceability, the movements of a product shipment from 7 days, which you can see the number of seconds, to just 2.2 seconds. Then, at 2017, Maersk and IBM launched the TradeLens smart contract platform, which is a cross-border blockchain solution to optimize once more workflow operations, supply chain management it is, and it's focused on the reduction of delays and human error removal. They achieved 40% efficiency in a market estimated at around almost $2 trillion US, therefore saving time and in turn millions of US dollars. Now let's go to the hot part, which are the financial use cases. International asset transfers, the most common worldwide use of blockchain and smart contracts in general. It's a typical phenomenon that we face in our daily life. Each time we want to explain to someone what blockchains are, so we start, are you familiar with the blockchain technology? And of course, when the answer is no, we proceed. Personally, I proceed to the question, are you familiar with Bitcoin? And then we have a common basis to continue. Bitcoin, Ethereum, Neo, EOS, Monero, thousands of cryptos comprise a market which we call cryptocurrency market. It was less than a decade ago when smart contracts revolutionized the global norm with their fundamental encoded features, immutability, transparency, privacy, security, as Dimitris stated in the previous lectures. To date, according to tradingview.com, there's a daily circulation of 180 billion US dollars, while the total market capitalization is almost 300 billion US dollars. Since the peaks of early 2018, where one Bitcoin was estimated around $19,000, we're facing the bear market, a period of prolonged price declines. Aligned with the crypto market, financial services like banking appear to be very important in business arena. But why is that? By switching to smart contracts, banks and financial institutions can experience automated, accurate operations and processing, guaranteeing conformity to strict regulations and requirements. As Alexander Zelinsky, the CEO of Velvet Banking, a blockchain-based banking system, stated that by removing the people factor, we can remove the rate of human error and place full trust in this automated, secure system, which are smart contracts. Then, another important utility of smart contracts is the identity management. We do find great implementation of this asset in the healthcare industry. Similarly to supply chain management, smart contracts have the ability to streamline insurance claims and increase public access to cross-institutional data. Since information on the blockchain cannot be manipulated, as we've said, data are immutable, encoding and storing personal health records can ensure additional privacy and confidentiality. This can allow consumers to easily use and transfer their patient information if needed. On the health provider side, this decentralized ledger system can be utilized to manage drug and care supplies as well as test results. Smart contracts, on the other hand, can fix poorly managed patient data. How? In the work of Kriegs and others at 2018, as you can see in the relevant figure below, it was demonstrated that Ethereum smart contracts can automatically keep clinical anonymous data in a permanent ledger in order to utilize big data with more streamlined information, leading to more significant results. Sensors, hardware products were connected to an Oracle master device, which were transmitting data to a network of nodes and then onto the blockchain. Afterwards, smart contracts, which are the account holders that we said before in the supply chain approach, share the data and they control the type, the quantity, and the quality of information that is going to be transferred to additional identities, doctors, medics, government, etc. Finally, the question remains, through all of those sectors and axes, where the market is headed. Scientific analysis related to real-life use cases showed that during the last decade, publications regarding smart contracts appear to form two distinct clusters. The first is the market cluster, which gathers all the issues around security and privacy, and the other cluster is the applied one, where smart power grids distribution systems, natural resource management coexist. Once more, we believe as a team that this second cluster regarding applications will bring additional revenues and will expand even more the theoretical background with new ideas, cases, concerns, and challenging concepts and progress and products, of course. In a macro scale, entrepreneurial level, it seems that a new era will rise with the potential prevalence of smart contracts. Smart contracts applications can go beyond the optimization of the enterprise workflow. They can facilitate the integration of small, medium enterprises into cross-organizational work groups by creating this open access peer-to-peer environment to establish fair participation. With simple words, we will have two different groups in a common battlefield. The first group, the big players, big, strong companies already expanded and established, which are characterized by huge enclosed and centralized systems of information and services, which lead to conventional innovation. While at the second group, we have the small, medium enterprises, which strive to develop as individuals. Smart contracts can give the ability to small, medium enterprises to create their own peer-to-peer network of mutual trustless, no need for trust. Remember, mutual trustless collaboration in a distributed and decentralized manner, getting that way rapid innovation along with risk and cost reduction, and as we've said before, improved efficiency. Where smart contracts create maximum value. This is a very important figure that we have to remind ourselves in the beginning of every activity that we want to operate along with smart contracts. A successful project is one that gathers all the different advantages of smart contracts in an harmonic layer, which is better than traditional already existing applications. Firstly, smart contracts utilize decentralization as their main element. No need for trust already exists in the form of the transparent data. It seems that the most applications, 44% of them, choose smart contracts platforms primarily for this specific advantage, transparency. In addition with transparency, anonymity exists, so we can preserve privacy in order to upgrade market competitiveness or the security of our partner or customer's agenda. Immutability provides our ledger with permanent data as an asset of security for us and for our customers at the same time. Last, rapid enforcement occurs through the automation of transactions of data, a utility which improves actually trust between potential collaborators. There's no need for payment or delivery delay because they're going to take place rapid enforcement of penalties and thus prevents legal issues. All the above elements lead to reduction of complexity into business arena, combined with a reduction in the overall operational cost. The key, of course, is automation. In the next slide, we're going to see how we can approach an idea with the above assets in an effective way. According to the Food Agricultural Organization 2016 data, Black Sea and Mediterranean region had a production revenue of $27 million US. In the eastern side of the Mediterranean, and we're talking about marine products, Italy holds almost a half of the revenues, while Egypt, Turkey, and Greece are notably players in the market too. As we've seen before, clusters of innovation in the field of smart contracts are constantly driven from theory to application. To date, the baseline is already there. Innovative approaches, for example, primary production, as we're going to see here now, can bring the challenge that the market needs. Through the approach of smart contracts and blockchains in general, we can identify all the freelancers as peers in the same network where they don't need the presence of an intermediary, of a third guy, to spread and to allocate their production. More specifically, Southern and Eastern Mediterranean region heavily lags in technological infrastructure that can host an operational network like this. Thus, every activity takes place traditionally. Traditionality actually does not stand as a disadvantage, but dysfunctionality does. Our team already working with a prototype called MaxiBlue. The main idea behind MaxiBlue, as you will see, is to host and at the same time optimize the blue marine production of the Mediterranean in order to maximize it. Every wise question, once again, is why should I use smart contracts instead of another common used interactive database? Why should I use them? Smart contracts can easily be abstracted to a holistic design. What do we mean by holistic design? Simply that every disadvantage that currently exists in the supply chain of operations can be approached and operated by an automated contractual agreement. In specific, in the use case of MaxBlue and the primary production of the Mediterranean, there is a large production with absence in the individual level and obscurity in the national level of data. Absence and obscurity of data. With the implementation of a homogeneous smart contract operational platform, transparency occurs. And thus, the solution regarding the lack of systematic data is solved. Additionally, another problem is the need for a ledger. Blockchain, as a continuous structure of data, provides an immutable ledger. In a transnational approach, this ledger can be utilized towards sustainable development and policy enforcement, reducing that way frauds, misresponding, and bad behaviors in the system. The data may be permanent, but the players remain anonymous for each other, so the need for trust does not exist. A vital functionality that is needed in competitive markets as we have now. Last but not least, traceability is an amazing asset that can be provided through the patent record keeping in the blockchains. With the use of GPS systems and the timestamp in smart contract transactions, we can solve this problem regarding identification and authenticity of each product type. Blockchain provides us with tools that are adapted to real-life problems and that seek solutions. But remember, do not find solutions for non-existent problems. A common sin entrepreneurial behavior, especially in the field of novel technologies such as smart contracts. Now I'm going to give you a brief explanation of the main idea behind the MaxBlue design, the number of smart contracts, the assets that will be used or under process to be used, and how the system can step-by-step reach a secularized, decentralized economy. We have six types of wallets in a similar form, like our initial blockchain abstract design. Here we have the wallet of the control sector, which is the government and the research sector. We have the production sector, where we have the environmental resources and the fishing vessels, let's say the industry. And now we have added wallets that represent the realistic market approach. We have the middle salesman and we have the consumers. In the consumers, we've achieved to end up with all the type of information that exists, and at the same time, information is everywhere in all the wallets, permanently, anonymously, immutably, and of course, with low cost along with the asset of traceability. How it's going to work in real life, of course, except the blockchain platform we will need to use special hardware equipment, for example, sensors, which can reach high security and protection of data, while at the same time, there is a rapid real-time monitoring of the transactions transformed into transactions onto the blockchain. Now, a very useful thing to discuss about is the human resource challenge, how to assemble a team. As in every good technological project, good development depends exclusively on the team behind it. The selection of partners in this novel and immature business arena will predefine the success of the application. During the beginning of a project, and this is at the technological readiness level of 1, the team should focus on architecture and design, followed by methodology of the implementation, which can be explained in a TRL level 3, 4, and 5. In this phase, an optimal ratio of human resources would and should be at the ratio of 3 to 1. 3 programmers and engineers that will establish and set the code of smart contracts. 2 field experts, for example, related and connected to the use case that you will select. In our case, that we will work with marine exploitation, probably going to be researchers, probably going to be financial scientists. And of course, you need the ratio of 1 market expert. Afterwards, when the project will be established, your focus should shift towards the testing and the expansion of the system, which is in a TRL level of 6, 7, and 8. Then we keep the same team while we expand the market departments. We're going to have 100-degree inversion of the ratio to 3-to-1, 3 market experts, 2 field experts, and 1 programmer engineers that will keep and maintain the whole platform. Some words about BaaS. BaaS is blockchain as a service. BaaS solutions are offered by large industries towards enterprises that want simplicity. What does it mean? They allow the users, an entrepreneur investor that has an idea to develop, use, and host their blockchain apps, especially their ideas, to host them in apps and functions through smart contracts. The affirmation ratio that we've said before, 3-to-1, can dynamically change to just 1 investor and 1 BaaS operation. You don't need all the structure, you don't need all the design, you just pay this service and you solve all of your problems. Blockchain as a service, it's a promising offering that helps enterprises to become future ready with scalable solutions built on the blockchain technology without, of course, getting too much into the arena. The above factors will help you to decide, and I'm discussing about the whole design and structure, or if you're going to use the BaaS solution in order to implement your idea. But of course, it depends on the case. If you're a traditional businessman, and if you're not that familiar with technology and innovation, probably it's optimal to use a BaaS service. But if you want to have a startup approach and a new idea, you need to invest in knowledge. You need to find the insight of smart contracts. You need to work with them and not just keep them by using a BaaS service. Now, the importance of networking in this novel market of smart contracts. In order to succeed in this immature market, there are some steps, some specific steps that you should follow. First, find your entrepreneurial allies. Regional collaborations with high quality of companies which match the goals of your implementation and share the same vision of yours will help you to make a wider network. Widely used smart contract platforms will advance this step. The 50% of the applications until 2018 were running under Ethereum smart contracts and Hyperledger Fabric. Then, please attend to worldwide conferences and exhibitions in the whole world. Every month, numerous companies and organizations gathers and discuss about current trends and promote innovative prototypes. Only for 2020, prior, of course, Corona period, 72 blockchain events were supposed to take place. Then, as a third step, research and organizations and collaborations with academia will help you to get even more expanded. To date, it is a solid fact that most smart contract applications used in business, and the percentage is 87.5%, have been under peer-reviewed scientific papers. Finally, after the 3 steps, national and EU public collaborations, which is a major step. We think that is a major step to establish successful integration of your project as a key player in the field of blockchain and technologies. Very briefly, we're going to highlight the 2 most common funding tools of the previous months in the EU. The first, the call for DLTs, which are distributed ledger technologies for social and public good. There was a big funding tool, which was estimated to a budget at 700,000 euros, and it could be worked as a transnationality inside the teams, 7,000 euros per team, but now it's expired. And right now there's the CF blockchain call, which is still active, and the budget is higher. It's almost at 3 million, and the budget for each team, it's 150,000 euros per member state. And of course, there's a high co-financing rate. You can see it's 75% of total costs in each project. Very briefly now, legal status surrounding the use of smart contracts. We've looked the legal and regulatory framework of blockchains and smart contracts. This was a book that was published by the European Commission last year. And we've tried to abstract the main problematics that they observed. The first thing is that they want to characterize and categorize crypto assets. They finally found 3 different types. The first one are the payment, exchange, and currency tokens. We're talking about virtual currencies, or as we know them, cryptocurrencies. The other are the investment tokens, which are meant to raise capital or provide ownership. And let's say investment tokens, a type of them are ICO, as we know them, initial coin offerings. And then we have the utility tokens, when let's say the tokens that we use in our previous ideas, which enable access to specific product or service on the blockchain to be used and to be circulated. The second problematic that they approached are the DAOs and their entities and their existence. DAOs, as we've said before, decentralized autonomous organizations. We have 2 different types. The first type are the DAOs that are registered in some jurisdiction and are compliant with the current legal rules. But of course, we have the opposite, DAOs that are not registered anywhere, they're not compliant with regulations, and they provide different levels of privacy and anonymity, and of course, transnationality most of the times. And the third problematic is a more dystopic topic, is the connection of smart contracts that can act as autonomous agents. We have issues as artificial intelligence, as features of machine learning inside smart contracts, and the theme of a smart contract as a legal vehicle, which can cause fiscal repercussions. We're not going to talk about this because it's highly specific, and so these are the main approaches by the EU Commission last year. Now, the compliance with current EU legal framework, we're going to talk about the GDPR assumption, the GDPR, the European Data Protection Law, that was published 4 years ago. The first assumption connected with as a problematic with smart contracts is that the first assumption of GDPR is that there is at least one natural or legal person that data subjects and can address and enforce their rights under the EU data protection law. We have in smart contracts and in blockchains in general that seek decentralization, we strive to replace an actor with many different players. This makes the allocation of this responsibility and accountability of natural legal persons burdensome. We don't have specific targets when we want to accuse someone. The second assumption that is against the main smart contract idea of the GDPR law, of course, is that data can be modified or erased when necessary to comply with legal requirements. We see that blockchains render such modification of data impossible to ensure data integrity and increase trust in the network, in the whole network, determining whether distributed ledger technology may nonetheless to be comply and is burdened by the ancient definition of erasure. We see that we have different assets as mutability, as permanent storage, and this is in contrast with the GDPR law protection, which is a trend right now in companies and in governments in general. Code law, a general concept in the law societies, the legal societies. Code and law are human creations, and as such, we should approach them and respect them at the same time. Law is ambiguous, so that it can be more easily applied on a case-to-case basis. In contrast, code is extremely strict, and it should be enforced if it's coded to do it. So we have this difference, and I will close with some, for this sector, we're going to the challenges right now. I'm going to close with some words of the Dr. Lawrence Lessig, who is a Harvard professor, and he was one of the founders of the Creative Commons. The code will present the greatest threat to both liberal and libertarian ideals, as well as their greatest promise. We can build, or we can architect, or code cyberspace to protect values that we believe are fundamental. Or we can build, or architect, or code cyberspace to allow those values to disappear. So it's in our hands, and we're talking about an immature industry right now that we should be very cautious. Now, the major challenges, and this is the last part of my presentation, the major challenges in the smart contract arena, 4 major challenges. We have the creation challenges, where we have initially our code to the deployment. We have the deployment challenges from the deployment to until the stored onto the blockchain. We have the execution challenges, which determine the final and usable state of the contracts. And we have the most serious and severe challenges, the completion challenges. After the execution of a smart contract, the modification to the system state will be packed as a transaction and broadcasted to every network node. This proliferation of smart contracts can bring additional security and privacy issues, which can lead to scams and frauds. Which type of scams? 3 distinct types. First, phishing scams. These are the most common type in, or at least in the Ethereum smart contracts. In simple words, the victim receives a regular email or any other type of message that tricks them into sharing sensitive personal information. For example, their identity, their wallet keys, in order to access to login access to their Ethereum wallet. Then we have the Ponzi, or the exit scams, which promise investors very high returns in exchange for an initial investment. Returns are paid out of new investment funds to attract additional investors until the scammers suddenly disappear when you have a bank run. Then finally, we have the ICO exit scams. In these type of scams, criminals set up fake companies and then raise capitals via unregulated initial coin offerings, or ICOs, as we've said before. Once the ICO is completed, as we said, completion challenges, they intentionally cash out. Actually, they leave the investors with nothing but worthless digital tokens. So we should be very careful in these 3 different types. Then we have the risk of asset loss, a new trend towards a more proactive approach has surfaced. Attackers don't search anymore. Just a second, I'm sorry. I'm sorry for we were talking about the risk of asset loss. There is a new trend towards a more proactive approach that has surfaced. Attackers don't search anymore for vulnerable contracts. There is a new trend that attackers lure their victims into traps by deploying seemingly vulnerable contracts that contain hidden traps. Their name, honeypots. But we have the honey badger, which is a symbolic executional tool that is employed and by well-defined heuristics, trials and error searches, which expose these type of honeypots and manage to have an 87% of accuracy. Very briefly, an analysis showed that it's very accurate and found in some specific smart contracts a huge amount of frauds that almost reached $100,000. So be vigilant out there. It's very important. To close, a very important report, as you can see in the bibliography, about the scams in blockchain technology, and especially in smart contracts, and especially in Ethereum smart contracts, so that in 2019, scams comprise the most of cryptocurrency-related crime, which was estimated around 8.6 billion US dollars. The 3% of the total blockchain amount. In fact, if it weren't for just 3 large-scale Ponzi schemes, scams would only account for 0.46% of all cryptocurrency activity. These Ponzi schemes were accounted for 92% of total scams in the crypto market. And the noteworthy fact is that blackmail scams increased 4 times in total revenue compared to 2018 to 22 million US dollars. And this may be a deterring factor that may keep new investors away from entering the blockchain community. Here you can see our bibliography and, of course, our media attributions. And I think now I'm just in time, 15 minutes, and it's time for the Q&A session. Thank you.
So thank you very much, George, for the ending of the presentation. Yeah, I think you were just in time. We will now hold the Q&A session, if Claudio also agrees with me.
Yes, sure.
So, well, feel free to ask your questions. I do have 2 questions already from people earlier.
And Dimitris, I have a suggestion. Since I've seen that Kyriaki published 1 hour ago the form for the test, maybe you can also comment on that and check if someone has filled it. At least in the morning and yesterday we kind of discussed the solutions.
Well, absolutely. Well, my colleagues from Gnomon, Corina and Spiros, have also published some self-assessment material, some questions for self-assessment. So for anyone attending this conference, and if you would like to test your own knowledge on the material that we've presented here, we've also included some easy, medium, and hard self-assessment questions that are created to quantify how much you understood of the classes or not. We will be honored if you could complete those. It's useful data for us to see how people reply to these questions. Of course, there's no really... George, you're presenting, sorry.
No, just to the Q&A panel.
All right, thank you. And just so you know, there's no really, especially on the hard questions, there's no really absolute correct or absolutely wrong answers. So if you could fill up the Google form with the self-assessment questions, that would be a great help for us, for me, George, for Common Experts, Isabetta and Claudio, to actually fix up our material and make it better for future lessons. Because this isn't something that will end in just a single session. This will be something that will continue up until the end of 2021. So our material needs to be dynamic, and we need to judge how well viewers understand the material. So if I can begin by answering the question of Mr. Damio Samaruga, I hope I pronounce your name correctly. As I said, I'm not Italian, I'm Greek. I do not speak Italian also. Mr. Dario, you've asked me, thank you, that you have some doubts about the procedure to recall a smart contract by users that want to use it. It's not clear to me how this happens. Well, basically, what you need to consider is that to recall a smart contract is not really viable. Ahead of time, you need to actually make it so that when you need it, when something goes wrong, that you can actually lock up or suicide your smart contract or kill it. That's what we mean by killing a smart contract. Usually this doesn't happen. And if you actually have some time to react, if you have the possibility of shutting down your own contract or pausing your smart contract, you are considered lucky. Usually when an attack happens, you either lose everything or your smart contract locks up forever. So a locked smart contract is still alive, but it's a zombie. All new calls to it fail, and it can never do anything. It just becomes, how can I say it, immobile, stagnant. This is usually what happens when you attack a smart contract or when your smart contract breaks. So it is very rare, and you are lucky if you have enough time to disable or to kill a smart contract. Even if you do, the history of every transaction towards that smart contract can never be erased. This is the basis of the blockchain. So usually when developers outgrow their smart contracts, when their business outgrows the needs of a smart contract, they usually just ignore them. They deploy new ones. Maybe you can kill the old one, maybe you don't care enough to do, and you just direct the new users to the new smart contract. And that's the process. Usually you don't kill smart contracts. You just put them up on an address and just lock them forever. And of course, the history remains fully. To fully answer your question before finishing up here, there are some ways, some design patterns for programmers and for development teams that if we can, there are some ways to build expandable smart contracts that can change themselves. Let me tell you, these are extremely complex smart contracts. And if you're starting right now, we're talking about the need of at least of 2, 3, 4 programmers to actually make use of smart contracts like that. So it's usually of a use now, throw away later kind of tactic, just because smart contracts are so immature yet. But of course, larger systems exist, but it becomes very complex very easily. Mrs. or Mr. Andrea Grigoletto, he asked that, is CaptureTheEther.com a good platform to start practicing with smart contracts and their security? I'll also take these questions, George, if you allow me. I didn't know CaptureTheEther.com. I have to tell you, I Googled it just now. I just saw it. It seems to be like a sort of challenge game or a website of smart contract challenges so that you can teach yourself about security issues. Let me tell you, this is great. This is absolutely great. I love gamifications like this. I love that you challenge yourself to learn better about the challenges on a smart contract development platform. And for me, and I totally agree with you and what you posted, if you try to find security holes or to learn about smart contract security by trying to break smart contracts, it's the best way to actually learn. One thing to consider, please consider that Ethereum is constantly patching itself. And on the website that you posted, I saw that most of the smart contracts were for very old versions of Ethereum. So maybe the attacks that you see right now are probably fixed or not possible anymore. So make sure you're not learning stuff that's already fixed. That's the only thing. But still, it looks great. And teaching yourself about security through games is absolutely fantastic, especially for developers. No problem. Another question by Andrea. I've got another question. Can we put a multi-signature feature to the suicide function? Absolutely, sir. You can absolutely put a multi-signature feature on a suicide of a smart contract. And in fact, me and George, in our smart contracts, we always put multi-signature suicide functions because I don't want to wake up one day and see that because George is mad with me, he suicided the contracts up on the system, or vice versa. So yes, Solidity for Ethereum at least is Turing complete. So all the logic that you can imagine can be implemented through code for sure.
Can I add some words?
I'm sorry?
Can I add some words?
Sure,
please?
Absolutely.
Regarding potential investors, I want to highlight something. I saw your questions, and probably there will be more questions in the forums. So at this phase of lessons, I think that we should focus on the code design of each smart contract. I'm talking regarding investments. holes, the security gaps, discrepancies in the code design may lead, or as you said, mostly lead to scams. There's not such thing as rapid revenues. There's not such thing as crypto unicorns. You should be very cautious depending the code behind each smart contract. Either as a technological infrastructure, there are utilities, there are functionalities that you can invest on them. Everything is deterministic. It's not like regular casinos. It's not a casino. It's technology is science. This is what we want to highlight. There is code behind. There are programmers, scientists behind, and thus development and evolution of this industry will occur. Otherwise, we're going to be full of scams and frauds until the end of this wave of the blockchain wave technology.
Some other more technological, more technical questions again. Mr. Matteo Riva, he asks that if it's clear that a smart contract is a piece of code stored on the blockchain, what is not clear for Mr. Matteo is where the code is actually executed. Where is the execution environment, and is the Ethereum virtual machine, does it belong to the blockchain network? Yes, the virtual machine belongs to the network because it is an integral part of every node, every machine that runs on the Ethereum network. If it helps you understand it this way, if you open up an Ethereum node on your own computer, if you run the Ethereum client on your own computer, your computer will start executing and calculating smart contract transactions with someone else. So every computer that participates on the network takes a little bit of the computation time and executes smart contract code itself. Now, all these computers, every single actor on the network, miners, normal users, clients, everything that happens, they start calculating the smart contract results, and then they match the results together on this environment that we call the Ethereum virtual machine. And then they match it together and they validate it. So every computer, you can think of it this way, every computer on the blockchain network executes the smart contracts, but the environment of this execution is, because it is sandboxed and clearly bordered, is called the Ethereum virtual machine.
Thank you. Thank you very much.
No problem at all. Thank you for your question. And by Mr. Giulio, if I can pronounce that correctly, he has a question. I know gas is necessary as the system is autonomous. However, at the moment, the price Ethereum is too high, for example. Games like CryptoKitties, of course, have become unplayable because of fees. How can the system be viable if price can't be controlled? There is a common misconception, Mr. Giulio, sorry, and I would like you to focus on that, is that most of the clients for Ethereum wallets that exist on the marketplace right now are not made for programmers or are not made to give you full control. If you use the Ethereum client from your machine, the official Ethereum client, you can pay as low as 0 gas per transaction. So it is completely up to you to, as we said in the presentation, to pay as much as you want, which of course, if you pay one way per transaction for the gas, maybe your transaction is going to be a little late. I mean, it's going to stay in the pool for maybe a day. If you try 10 or if you try 15, it's going to get executed much faster. But common wallets out there in the web, common wallets, because they don't give you the capability to actually control how much you're paying, they usually overcharge you, just so that you do not complain that their service is not working and that their service is not really fast and it doesn't get your transactions out of your wallet. They overcharge you 80 or 100 way, which is an extreme amount by programmatic standards. They overcharge you just so you will never complain that your transactions are late, which of course makes people think that the gas cost for the network is so high. No, it's just a service fault by the services themselves. If you download the Ethereum client yourself or any other official blockchain network client yourself, you can control absolutely exactly how much gas you're going to pay, and you can absolutely control that. Okay, but I absolutely agree with you. Games like CryptoKitties, they raise the fees. They raise the fees, exactly. But because the cost goes up, you're supposed to pay less gas, but these services do not update themselves. Maybe some services take a little bit of the gas fee for themselves. Look into that also. Thank you for your question. So if nothing else is coming up or being presented, please do know that we're going to be sharing the material with you also. Feel free to send them via email. We will answer everything, even if it's very specific. Hey, I'm trying to code this. How do I do this? Even technical questions, even business questions. Is this viable or not? We will be happy to answer your questions, no matter how specialized they are. So feel free to send an email to Ms. Elisabetta. She'll do the clear up of the questions through Common Next. Is this it?
Yeah, thank you very much, Dimitris and George.
Thank you for having us. Thank you for having us.
Thank you. So we can start the recording. I mean, I don't know if there are some last questions, but it's been a long day for us.
Absolutely.
Yeah.
And
We've just been here 3 hours. We've just been here 3 hours.
Yeah, especially for the participants. So thank you very much for staying with us until the end. And you will receive updates from us next week, most likely.
Correct.
Okay. Thanks a lot.
Thank you all.
Bye, everyone.
Thank you very much.
Bye.
Please don't forget the self-assessment questions, everybody. Please, please, if you have time, please fill them up. Thank you very much.
Yeah, in the follow-up questionnaire, in the follow-up email, we will send all the links, because we really need also the satisfaction questionnaire to be filled. So we will take care of that.
Thank you.
Thank you.
Thank you very much for having us.
Thank you. Bye.
Bye-bye.